the Ventura River Watershed Coordinator. Welcome. We're so excited to share our climate study with you. First, before we get started, I want to introduce you to our core team. Lynn Rodriguez from WCVC, you guys all know. Laura Meeker, from who is the Santa Clara River Watershed Coordinator, is here. And Brian Stark from the Ojai Valley Land Conservancy. And our two amazing researchers, Dr. Nina Oakley and Dr. Ben Hatchett. Just a little history before we kind of dive into the information. The Resource Legacy Foundation, which is kind of a granting agency, reached out to Lynn about a year ago last winter, looking for project proposal ideas in the Ventura County area. At the time when we were in discussion, we decided that, what we really need is a really great climate study to bring some of the concrete information that we can use to, number one, update the Integrated Regional Water Management Plan. And number two, really bring in some of the solid data point and information that we need about our climate future in the Ventura County area so that we can really start to have some of the harder discussions about planning and adaptation to climate change impacts. Some of you know within my watershed, I actually worked for NOAA, the National Oceanic and Atmospheric Administration, for about 11 years in DC, and worked with a lot of drought and climate specialists. And so when this study kind of came about, I reached out to one of my colleagues who very quickly recommended me to Dr. Oakley. And upon talking to Nina, I realized why. Number one, she was somebody who specialized in the California area. She's worked in studies in Santa Barbara before. And she really knew some of the needs that we had in terms of what are our biggest vulnerabilities in terms of water resources, fire risk, et cetera, et cetera. So we're really excited to have her and Ben here to really share their work with us. And we feel really fortunate to have this worked out so quickly, actually. Lastly, I did want to thank the Resource Legacy Foundation for funding this. Obviously, without their dollars, this wouldn't happen. And second, to Brian Stark. He's been instrumental in managing the financial aspects of the grant and also really providing a lot of help when we were filing our grant application. So thank you. With the Ojai Valley Land Conservancies. Yes, he's wearing the t-shirt. And so last note before we get started, this session is being recorded. But please ask your questions. And number two, we'll be sharing the presenters' presentations and notes with you after the meeting. Without further ado, here's Nina.
Hello, everyone. Oops. Try not to run into anyone here. I'm going to get up on the stage so I can actually point things out as we go through this. So the purpose of my presentation will be to go through and give some background, a review of the literature that's been done pertinent to climate change in Ventura County. I'll be setting the stage for Ben Hatchett, who will be talking about some of the actual results we've done, the analyses that we've done so far, and the analyses we plan to do as part of this project. And the purpose of both our presentations will be to stimulate ideas and questions and what kinds of climate change thresholds are important to you, what information do you need, and get you asking some questions so we can, through our remaining research contract, fulfill the needs that you folks have in prioritizing for the IRWIM plan and in your climate change adaptation planning. So just to give a little bit of background on myself, I'm from Santa Barbara County originally. I did my bachelor's in geography at UCSB, went on to get my master's and PhD in atmospheric science at University of Nevada, Reno. Growing up in Santa Barbara County, got to see some fantastic floods in my youth, and that got me very interested in weather and climate and extreme precipitation. And I was fortunate enough to get to study Southern California extreme precipitation for my dissertation work. Most recently, over the last couple of years, I've been working on post-fire debris flows and shallow landslides. So the Montecito debris flow last year was it was tragic, but also interesting from the research standpoint. We were able to learn a lot from that event, and I'll be talking a little bit about that as well. My official title in my job is a regional climatologist, so I work on these short duration, high intensity precipitation events as part of my research, but I also work in climate services, providing climate information to people to support their decision-making needs. So that's really interesting to me. I generally work with the last 100 years of observed data, and I work at a place called the Western Regional Climate Center. We're a NOAA agency, so you're probably very familiar with the National Weather Service. We're kind of like the climate side of the National Weather Service. So there are many climate issues facing Ventura County. We're really going to focus in Ben and my presentations on these first four, on temperature, precipitation, extreme precipitation and flood hazards, and changes in wildfire characteristics. There will be other groups coming along from the state working on surface and groundwater changes, and sea level rise is starting to get a little bit out of our area of expertise. So we'll be focusing on these first four. In my presentation today, I'll go through temperature very briefly. Ben's going to talk about that in more detail. I'll talk about precipitation change, projected precipitation changes, and also some of the challenges that the models have in simulating them. High intensity rainfall and flash flooding, wildfire in a changing climate, and summarize everything at the end. So looking at temperature, so this is, we'll go kind of step through this graph. This is looking at maximum temperature. At the bottom here, you have this. You'll see, you can barely see it on this particular screen, but this gray shaded background. This is showing the envelope, the extent of 32 different climate models, the range that they show for the historic period and also for the future projected period. This is from 1950 to 2005, and 2005 out to 2100. And then the dark gray line is the actual observations, and this is for the Ventura River watershed as an example. And then when we move into the projected area, you see there's four different colored lines here, and these represent four different climate models that are of the 10 best climate models that have the best representation of California climate. These are four that help show a range of possibilities. And so the interesting thing, the thing I want to point out here is that while we see variability among these four models and among the envelope of the 32, all models agree that for maximum temperature, we see a significant rise. And this is using what we call the business as usual scenario. This is the representative concentration pathway 8.5, if that means anything to anyone. And this is the path that we are currently tracking on. So we can shift to minimum temperature, and we still see that same model agreement of all models agreeing on a rise in minimum temperatures. Something a little bit different about this graph than the maximum temperature is already in the historic period, we start to see an upward trend in minimum temperatures, and this is something we've noticed at many places in the western US, that there's a significant upward trend in minimum temperatures, but we don't, if we flip back to the maximum temperature, you see a lot more variability in the historic period and not as pronounced of a trend. And so the rising temperatures are really important for the context of the rest of the presentation, as these increasing temperatures are driving evaporative demand, so like the thirst of the atmosphere, how much water wants to evaporate in the atmosphere, which is going to increase evaporation and have impacts on the landscape. So moving into talking about precipitation. So same type of graph that we saw in the previous slides for minimum and maximum temperature, but for precipitation. And so you can see that we don't see, either in the historic period or in the projected future period, we don't see any real agreement among the models in precipitation going up or down, but we do see, as we move from the historic into the future period, increased variability. The lines become more squiggly as we move into the future. And so the next few slides we'll spend a little bit of time talking about why that is. So Southern California exhibits some of the highest precipitation variability in the nation. So these darker blue colors mean there's more interannual variability. We go from a dry year to a wet year and back again, much more so than anywhere else in the nation. We also see some of the highest storm totals in the nation in Southern California. This map is showing weather stations with 3-day precipitation totals at weather stations. The red dots indicate 3-day precipitation totals greater than 500 millimeters. And so you can see across the transverse ranges here, we have 3-day precipitation totals that are on par with what we might observe associated with hurricanes in the south and southeastern United States. And many of these extreme events in the transverse ranges are associated with atmospheric rivers. And so we'll take a little look at atmospheric rivers, talk about these for a moment. So the graphic that we're looking at, this is the first couple months of 2017 when we had several atmospheric rivers impact the western U.S. These green and yellow colors are areas of high water vapor transport. So many of you are probably already familiar with the term atmospheric river, but if not, these are narrow corridors of high water vapor transport, moving water vapor from the subtropics to the mid-latitudes. And these are often associated with large precipitation totals or flooding throughout California. And because these features move so much water vapor into the western US, whether we do or do not get just a few of these atmospheric rivers really impact whether we have a wet, dry, or near average year. So looking at this in a little bit more context, I'm going to share with you some work we did on the San Ynez River Basin in Santa Barbara County. Sorry, I don't have an example for Ventura, we'll get there. But we took an average of 6 different weather stations in the upper part of the San Ynez River Basin, and we looked at interannual precipitation variability and its association with large storm events. So looking from water year 1966 out to water year 2017, we categorized each year as being wet, dry, or near normal. Precipitation totals that were in the upper quartile of the historic record were considered wet years. Those in the lower quartile of the observed record were considered dry years, and those are shown in yellow. And those that had precipitation totals in the interquartile range are depicted as white, and we called those near normal years. And the graph is showing departure from the median, the 1981 to 2010 median. And so we can, if we click one more forward, we also put Lake Cachuma June 1st storage, so end of the wet season storage here. And so you can see that with just one dry year, we see quite a drop in storage. There are a lot of variables that go into reservoir storage, but with multiple years, multiple dry years, we really see a precipitous drop. And then just a couple wet years can really bring the storage back up. And so you'll see some of your favorite dry years, the recent drought, the 87 to 92 drought here. 2007 was a particularly dry year, and wet years, 1969, very wet year, 1998, 2011. And just barely making the wet year category in water year 2017. So then we wanted to look at, so in these wet years and dry years, what's making the difference in terms of big storm events? And so we defined extreme events as events that were greater than the 90th percentile in the station records. These are storm events, so they can be multiple days of precipitation broken up by at least one dry day. And so when we look at the contribution from these extreme events, and unfortunately the text isn't showing up too great here, but on average, the wet years, the green years, had on average 3.3 large storms. Normal years had on average 1.3 large storms, the white bars, and dry years had on average 0.5 large storms. And we looked at what guarantees you having a wet or dry, wet, normal, or dry year. So if you have greater than or equal to 4 of these large events, you are guaranteed to have a wet year. If you have greater than 2, you can have a normal to a wet year. You're not going to have a dry year if you have at least 2 of these events. With 0 to 1 of these big events, you can have a dry to normal year. Normal is the best that you'll get if you only have one event. And about 3/4 of these events were associated with atmospheric rivers. So what this shows us is that the difference between a wet, a normal, and a dry year is just a couple of these big storms. And so this is important to consider when you're looking at seasonal outlooks or when you're considering climate change projections, that we need to consider the model's ability to capture just 1 or 2 of these storms. And including an extra or failing to capture one can affect whether you're getting your outlook is giving you the correct information. So looking at model depictions of Southern California precipitation changes. These are pulled from the 4th Assessment Statewide California document. And looking at the late century change from the historic period for an average of 10 models. When we look at this is for the RCP 4.5 with mitigation efforts and our business as usual that we looked at earlier, either way you go, you see a very small, actually, the model average shows a small increase in precipitation for the Ventura County area. And we all go, yay, isn't that great? We're getting more rainfall, we really need it. But as we talked about at the beginning of the presentation, combined with those above normal temperatures and the increased evaporative demand, any slight increase in precipitation will be overwhelmed by those temperature changes. Also, the model average shows a slight increase in precipitation, but when you look at each individual model, there is disagreement among the models in both the sign, positive or negative changes in precipitation, and the magnitude of the precipitation changes. And some of the ways that the models struggle with precipitation in Southern California are likely related to this reliance on just a few storm events to produce a wet year or a dry year. And so so as far as the magnitude and the sign of precipitation, we have a lot of uncertainty about that, but what we do have a bit more clarity on is the changes in the characteristics of precipitation. And one thing that we see in the models is changes in the number of precipitation days. So these figures are showing the change in 0 precipitation days and as a percent. And so for the Ventura County area, we see about a 2 to 3% change in number of precipitation days. So great, and if we want to actually put some numbers to that. So a little scenario here. So let's pretend, and it's probably about correct, that we have approximately 350 dry days a year in Ventura. All precipitation falls across about 15 days. So a 2 to 3% change in dry days would mean 7 to 10 days less of precipitation. So yet we saw in those model projections that they weren't having a large change in precipitation or were showing a slight increase. And so if we decrease the number of days on which we're getting precipitation but don't change the total amount or even increase it, this means that we are getting more precipitation in fewer days. And this is achieved through stronger storms and greater vapor transport. And we'll look at this in a little bit more detail on the next slide. So atmospheric river, here's a example of one in February of 2017. So what the studies that are looking at atmospheric rivers in climate models have found is that anywhere from a 20 to 60% increase in the frequency of atmospheric river conditions along the West Coast. And when we say increased frequency of atmospheric river conditions, this doesn't necessarily mean that there are more atmospheric rivers. What this means is the atmospheric rivers that occur are longer and have higher water vapor transport, so that at any point along the coast where an atmospheric river is hitting, you have persistence of those conditions within a particular atmospheric river. The studies are also finding that, that there's about a 10 to 30% increase in the strength of the moisture transport in the atmospheric rivers. And one study that looked at them globally found a 10% decrease in atmospheric river activity in the number of atmospheric rivers around the world. And so summing that all up, we are anticipating in a future climate fewer but stronger and longer duration atmospheric rivers in Southern California and the southern mid-latitudes, and also a potential for more individual years with more atmospheric rivers, and then more years with fewer atmospheric rivers, more dry years. So more of this going from a wet year with multiple atmospheric rivers to a dry year, as you saw in the high variability in the precipitation outlook. Another thing that's relevant to mention for Ventura County is the reduction in Sierra Nevada snowpack. So this is the Sierra Nevada, it's just at an angle, north is this way. And this is a study done by UCLA that looks at the reduction of the April 1st snow water equivalent, so how much water is contained in the snowpack, based off the future period of the late century, 2081 to 2100, compared to a 1981 to 2000 baseline. So they see a 64% decrease in snow water equivalent by the end of the century, and not only will you expect a decrease in snowpack, but also a change in the runoff time of snowpack, with snowpack melting earlier and running off earlier. This impacts its reliance as a water supply source, as an additional water supply source for Ventura County. There are some work underway to study changing the way that reservoirs operate, so that right now when the reservoirs act in both flood control capacity and storage capacity. And so in the winter and spring, when you can still expect big storms, the reservoirs need to release water and stay below a certain level and leave room for floodwaters to come in. But our weather forecasting has improved to the point that we can see a big atmospheric river storm coming ahead of time. So the question with this forecast-informed reservoir operations project happening out of Scripps Institution of Oceanography is, can we forecast well enough to hold our reservoirs at a higher level, and then we don't need to make releases unless we see a big storm coming? And that might be one adaptation measure to capture some of this earlier snowmelt runoff in a time when usually we'd have to keep the reservoir low enough to allow for stormwater flooding to come in. So moving into high intensity rainfall and flash flooding. So Southern California, it's part of the climate here is to see high intensity rainfall. It is a characteristic of the transverse ranges. And so this graph is showing high intensity precipitation across California for weather stations. And so it's showing all cases greater than, this should be a greater than sign, 15 millimeters per hour during the period 1995 through 2016. So this is about 0.6 of an inch an hour. And so we're looking at the size of the triangle represents the count of cases over this 0.6 inches an hour threshold, which is, this comes from a study on shallow landslides, and so this threshold was pertinent to landslide triggers. And so we can see some of the largest triangles, the most frequent cases of exceeding this threshold are in the transverse ranges. And we also see the color represents what fraction of those events are associated with atmospheric rivers. About 60% to 70% of these transverse range events are associated with atmospheric rivers. So,
what was the Montecito threshold? Do you remember the
The 15-minute, I think I have it a little bit later, yeah, but 15-minute I think was 0.8. The threshold is about a 1/4 inch in 15 minutes, the threshold for triggering debris flows, and I think it was about 0.8 in 15 minutes, but the highest 5-minute was 0.6 inches in 5 minutes. So see if I have the 15-minute value in here somewhere. So thinking about these short duration precipitation extremes in a future climate, this is a study done by Andres Prien, who's at NCAR in Boulder, looking at across the continental US. And he's looking at, in this study, in a future climate compared to a baseline 10-year climate period, the change in the exceedance of the top 0.05% hourly precipitation rate. So the very top 0.05 of extremes, how much more frequently do we see them? And so so this is for the December, January, February period. This is when Ventura County is going to see its highest precipitation intensities. This is based on that business as usual, so the projection we're tracking on right now. And so over Southern California, we are about 1.5 to 2 times more likely to exceed that top 0.05 extreme event in a warmer climate. And Ben will talk about this a bit more, that this study is great because it gives us at least something to start with hourly precipitation extremes, but there are some limitations to applying it. Post-fire debris flows in a future climate, 15-minute precipitation rates are really the best predictor of post-fire debris flows. And the study I just showed was on hourly precipitation extremes. Well, we found that hourly precipitation, it's kind of useful for post-fire debris flows, but really we want to get down to that 15-minute data is really critical to look at the change in threat for post-fire debris flows. And technology is there to look at 15-minute precipitation extremes in a changing climate. However, it's very computationally expensive to get at that, and it might take, just for Southern California, it may take a year to run the simulation. So no one's really attacked that yet, but we hope to in the future. These short duration, high intensity precipitation events are typically associated with very small features that are only a couple of miles wide. This is the radar image from the Montecito debris flow, and so you can see this narrow feature. This is called the narrow cold frontal rain band. So it's a narrow area of high intensity rainfall along the cold front. And it can be difficult for weather models, which tend to do pretty good on the few days to a week scale. It can be tough for weather models to pick them up, and they are well below the scale of the global circulation models, the climate models that we use. And so you have to do a special downscaling process, like the results of the study that we just saw, to try and resolve these kind of features in a future climate, which requires a lot of computation time. So moving on to wildfire. There's many factors that influence wildfire activity. Wildfire is a very, very complex topic talking about wildfire and climate change. So we'll go through it in just a few minutes, but I'm guessing there'll be some questions following up. So one of the drivers of wildfires in the future is increased population in the wildland-urban interface. So this is where you have the vegetated areas meeting up with where people actually live. And this figure on the left here is showing areas of new wildland-urban interface since 1990, and also persistent wildland-urban interface. And you can see across the transverse ranges, there's both new and persistent wildland-urban interface areas. Other factors that can influence wildfire activity are drought and insect infestations, invasive species, altered species assemblages. So do you change the type of vegetation that's on the landscape, which can be achieved through climate change factors such as warmer temperatures, especially at night. Those warmer overnight lows, the minimum temperatures, also impact firefighting efforts. Typically at night you have the temperature decrease decreases, and since temperature and relative humidity are related, as the temperature decreases, the relative humidity goes up. And this can help slow fire movement and allow firefighters to gain traction on fighting fires. But when you have the temperature staying warmer at night, it hampers those efforts a bit. Increased evapotranspiration can dry out the vegetation and lead to more flammable vegetation. Also, the increased frequency and magnitude of drought will affect fire frequency as well in a future climate. There's a recent study that points out the importance of, when we're talking about wildfire and climate change, we really need to look regionally in California. You'll see many studies that will group California together with the rest of the, Southern California together with the rest of the state or the rest of the West, but really we have special concerns in the transverse ranges in the Southern California shrublands. They describe the Southern California shrublands as an ignition-limited system. So each year, regardless of how much rainfall fell in the previous winter, we have a drying period over the summer. By mid to late summer or early fall, the vegetation has dried out and it's ready to burn. And this happens each year, regardless of what happened with precipitation the previous year. So every year we have a fire risk in Southern California. And so for climate change to shift this area towards more fire prone is unlikely because it's already fire prone every year. But what we anticipate is a lengthened fire season. And so that instead of the fire risk kind of tamping down around November, December as we get precipitation, for that to extend further into the late fall and early winter. But anthropogenic factors such as human activity, so people going out and recreating in the mountains or doing activities and lighting fires, are still a major concern here. So the human activity is a big factor in Southern California, which in some ways is a benefit because controlling and moderating human activity can be more tractable than trying to control the weather, the climate, the fuels. Santa Ana winds and climate change. This is some very new work. It's still in review from one of our colleagues' dissertations at UCSD. And very makes sense to talk about this right now as we're in the middle of a Santa Ana wind event that's ramping up. So what she found in her study was a reduction in Santa Ana wind activity. Overall, a 14 to 22% reduction across several different models that she found to perform best in capturing Santa Ana winds. So, so looking towards a future climate, decrease in Santa Ana wind activity and also decrease in Santa Ana wind extremes across all these models. And you can see some variability, but all of them show a decreasing trend. And what she found about the temporal, how these are distributed over the season, is that we have a decrease in the number of shoulder season events, so September-October events and April-May events, and more of a concentration of events into the November through March period. And so they propose that perhaps we have a narrowing of the fire season due to concentration of the Santa Ana winds into this winter season. We might have a narrowing of the fire season into November, December, January, say. Now, this doesn't mean we can't have we're not going to have extreme Santa Ana wind events anymore, that they won't happen in September and October, but her findings based on climate model output were that they will become less frequent in these seasons and less frequent overall. But that doesn't mean no extreme events. So wrapping this information together as a little case study on the Thomas Fire, as this is looking down, I think this is top of Cold Springs Canyon, looking down on Montecito after the debris flow. We saw we had a prolonged drought, desiccated, dried out vegetation, which provided ample fuels for the Thomas Fire. Some of the area burned by the Thomas Fire hadn't burned since the 1960s, since the Coyote Fire, which was 1964. I believe, and 1963. So we had all this ample vegetation. We had a very dry period, and then we had one of the driest starts to the water year on record. So by the beginning of December, there had only been a couple tenths of an inch of precipitation at some of the mountain stations, which is one of the 5 driest starts to the water year on record. We then had an intense and prolonged Santa Ana wind event in the beginning of December, and which allowed the fire to spread rapidly. And we had these old fuels from this area that hadn't burned since the 1960s. They burned at very high intensity, so you had well-developed vegetation and burned at very high intensity. One of the factors in post-fire debris flows is what your burn severity is. So when you burn at moderate to high severity, you greatly increase your risk for post-fire debris flows. And so we had the perfect conditions for that high-intensity burn in the Montecito area, in the mountains above Montecito, that increased debris flow susceptibility. Then we had this high-intensity rainfall event, that narrow cold frontal rain band I showed you earlier, which was not unprecedented for the region to have those high-intensity rainfalls, nor were among Santa Barbara County's weather stations. That 0.6 inches in 5 minutes didn't even set a record. The record, I think, is 0.73 inches recorded at UCSB in 5 minutes. So not unprecedented for the region, certainly extreme, but those narrow cold frontal rain bands, those high-intensity rain bands, are a characteristic of the Southern California climate. We don't know yet how they might change in the future. So putting all this information together, we have high confidence in increasing temperatures for the region, and these drive evaporative demand, are a key component of the drying, even though we see possibly a not much change in precipitation. There's uncertainty and model disagreement in precipitation averages, so how much will it increase or decrease? And this is likely dependent on that reliance on such a small number of events for defining a wet or dry year. We anticipate fewer but more intense storms and also more prolonged drought periods as we move into the regime of increasing number of dry days. And we hypothesized an increased frequency of these short duration precipitation, high intensity precipitation events, but currently really lack much information to say much about that. So that's an active topic of research, is what's going to happen to very short duration, high intensity precipitation and the atmospheric mechanisms that drive that. We see potential for increased length of the fire season with the way Santa Ana winds are shifting with prolonged dry periods. But Southern California remains ignition limited, meaning that it's going to dry out every year and just requires an ignition to get going. And climate change will enable wildfires, but climate change does not cause wildfires. So when we have this drying out of the vegetation, more vegetation growing, we set the stage for wildfires under climate change with this increased evaporative demand, but it still takes human activity in where people are living, in the way the landscape is managed, and whether people are lighting fires controls wildfire activity. And so thank you, and I think we're going to let Ben give his presentation and hold questions, because that'll give some more specific findings for Ventura County. And then we'll break and we'll come back and have a group discussion to take all your questions. So if you have a burning question, write it down and we'll get to it in the group discussion. Thanks. Do a quick switch over here. And close. From beginning. All right.
Cool. Well, thank you, Nina. That was an excellent introduction to kind of the state of the climate science situation for California, and in particular, Southern California. So what I'm going to share with you guys is some of our preliminary results from projections of 21st century Ventura County climate. And what we will first cover is I'll give you a little bit of background on global climate modeling and how we downscale climate models, and there will be a bunch of text, but the primary intent there is that I'll run through it, but then because you guys will have access to these presentations, so you'll be able to dig in a little bit further and kind of read on, get brushed up on exactly how we go from global climate models, which are at very large spatial resolutions, down to scales that are actually usable for all of you in your impact studies and trying to assess how things will change. Then we'll go into some of the examples of climate projections, taking information from the models and turning them from beyond average temperature or average annual precipitation to some more interesting, perhaps, calculations. And the intent there is that that will spur ideas of things that you might find interesting. Nina had mentioned, what are some thresholds that are of particular concern or interest to you? Hopefully this will give you some ideas as far as things that are possible to do with this model projection output. We'll give a little specific example on a heat wave that occurred this year with some notable impacts on the avocado and citrus industry and the native oaks of Ojai Valley, and then talk about a few of our next steps. So first, I'll give you a who am I, who's this guy talking to you guys up here. So I was born and raised in Northern California, but my family is from Southern California, so I got to be a little kid looking up at the San Gabriel Mountains, thinking that that was pretty cool up there, having no idea of the fires and debris flow hazard that were imminently above where I was playing around in the lemon groves. So I showed up in Lake Tahoe primarily to ski and maybe go to school a little bit. Got degrees in geography and atmospheric science there, studying past, present, and future climate studies. So we do a lot of work on paleoclimate, terminations of ice ages and megadroughts, and all the way into present climate extremes and variability, and moving into future applications for those. Predominantly in California and throughout the Great Basin. Specifically, a lot of the work I've done in Southern California has been on heat and cold extremes, sundowner and Santa Ana wind events, and then also helped out a bit with some of Nina's work on the precipitation extremes. So I kind of have a broad bit of experience, and I think it's really fun to apply all of those different pieces of information to trying to understand climate change in the future and how we can better adapt to that. So here's some of the wordy slides, so there will just be a bunch of text. Don't worry too much about that. Essentially, global climate models are our best tool to understand how the Earth system works and how it may respond to different changes, either in greenhouse gas composition of the atmosphere or changes in solar radiation, or you name it. This is the tool that we use to do it. It essentially works by simulating, using our best physical understanding of the key spheres, so the hydrosphere, the atmosphere, the biosphere, and the cryosphere. So we simulate the ocean, the land surface, the atmosphere, and the sea ice. And key goals in global scale climate modeling is that we really want to make sure that we're capturing the major modes of climate variability. We want to make sure that we have a seasonal cycle, that we have a warm and a cold hemisphere. Those are very important things, and if we get the seasonal variability correct, we know we're doing a good job. And so we start off at the seasonal scale, and we've almost got that. We're doing pretty well on that. The El Nino Southern Oscillation, the largest mode of climate variability on the planet, we're improving that. We're still not 100% perfect. Global sea surface temperatures and their distribution is kind of a present-day challenge. We're getting significantly better at that. And then an emerging challenge is the Madden-Julian oscillation, which some of you may have heard about, and that is a intraseasonal, so a 30 to 70 or so day mode of climate variability that's essentially an eastward propagating area of tropical convection. And we know that has a very strong tie to atmospheric rivers that eventually will make landfall in the United States or west coast of the US, as well as other weather and climate extremes throughout the world. As a result of computing power limitations, the models are very coarse in their spatial resolution. So how many model points can you simulate is still limited by the amount of computing that's required. And so that really limits the models in terms of local impact studies. We can understand large-scale circulation, how storm tracks or how atmospheric rivers may change, but we know that if I give you one number representing precipitation and temperature for Ventura County, you're going to run me out of the room because that's not realistic. That's not what's actually happening. And so that's the primary reason that we need a technique to go from this global scale model where we're simulating boxes that are roughly the size of Ventura County and take that information to a spatial scale where it actually captures the terrain and captures the nuances of say the marine layer versus a valley that has mountains in the way and does not receive that impact. The main difference in climate models and why they give us slightly different answers, they're all based on roughly the same set of equations to simulate the Earth system processes, but there are different techniques to solve those equations, and people have come up with different ways to approach problems that we don't have good equations that we can't actually analytically solve without great difficulty. And so we're approaching the same problem through many different ways. And so that's where we end up with the suite of about 32 models that are kind of generally accepted as good models, and why those all give us slightly different answers because they're trying to represent the same process through different ways. If we broke the room up into 10 groups of people and had you all solve one problem, we'd probably get a few different answers that would vary a little bit, but they all may be somewhat correct. The process of downscaling is kind of our best tool to apply to our best tool of understanding the climate system. And essentially what the point of downscaling is to take this global model output and make it usable for actual impact studies. Because if we represent the California climate in an original native grid, as we would say, scale, GCM, you can see these big boxes. So here's our region of focus, and it gets one value for Lompoc and say Ventura, as well as in the Central Valley. We know those are very, very different places, and that's not going to be very helpful when we start looking at, well, how will temperature change? And if the value of temperature change here in the future is, say, 2 degrees, we don't know if that 2 degrees is going to apply everywhere evenly. And so the goal is to shift this information to scales where we can use. And the process of downscaling does that. When you downscale this global climate model output and make it at a scale that is starting to be usable, we can see now that the major landforms are now being captured. You can see the Sierra Nevada shows up. You can see the coast ranges, the transverse ranges, the peninsular ranges. Things start to show up that we know are very important. And so essentially what we're doing in this process is transforming the coarse global climate model output into a finer spatial scale. There's two ways that is primarily done. One is called a dynamical downscaling approach, and that's essentially using the global climate model output to drive a numerical weather model. So when you get weather model forecasts from the National Weather Service, essentially what we can do is drive those same weather models with climate model output. We get very good results from that oftentimes. However, a primary limitation is that's extremely computationally expensive. We need a room this size or bigger sometimes of supercomputing resources to do that. On the other hand, what we are doing in the present study is applying a statistical downscaling approach, which is much more computationally efficient. You could all do it on your desktop computer, maybe even your tablet if you have a real new fancy one. And that's a much more simple, but still very, very effective approach that uses historical relations between the larger scale climate and the local observations to transfer the global climate model information to the finer scales. The problem, and we call it carrying an assumption that's probably a bad assumption, is that it really assumes that these historical relationships are between the local and regional observations in the historic period are going to remain the same in the future. And that's some call that the stationarity assumption, that this relationship will remain constant in time. We know that's probably a bad assumption, but really the only way you can get away from that is to use dynamical downscaling as well. And so the the very best studies will be able to apply both of those. And so that's a direction in the future that we'll probably try to go for this region as well, is to repeat a lot of this work with dynamically downscaled output. Another issue with global climate models is they'll often have systematic errors or biases. Precipitation overall might be 20% too low for a region. We need to correct that, and we correct that using the historical observations. We build this relationship between the historical relations and the model historical simulation, and we try to figure out how much that bias is, corrected in the historical period, and then apply that correction into the future. And so when we apply both of these steps, we end up with what are called bias-corrected, spatially downscaled projections. So if you ever hear that alphabet soup of fancy words, it's essentially taking this picture and turning it into this picture. An example of systematic error removal is if we take observations for historical December precipitation, and we look at the observations, and we look at what a climate model produces, we can see that there's some big differences in what the model is producing. And so this error here shows where those differences are the greatest or the smallest. And after you do this bias correction step, you can essentially remove all those errors, so there's no more of that error. And so these corrections are applied. We learn them in the historical period, and then we apply them in the future period. And that's where this assumption of stationarity can become troublesome, is because if those relationships change with time because of the circulations changing with time, we don't do quite as good of a job. But there's really no good way, no good easy way to get around that. And the statistically downscaled projections that we're using for the present study come from the LOCA product, which is developed by Dave Pierce and Dan Cahan at the Scripps Institution of Oceanography. It's called LOCA, or Locally Constructed Analogs. And it's an improvement upon the previously developed analog downscaling method approach. So for about 10 or 15 years, there was this there's a number of different statistical downscaling approaches. An analog method is one of those, and essentially what it does is it really aims to preserve the daily extremes and variability, because we know in a place that is has a highly variable climate, that's incredibly important to do. The technique essentially identifies historical days that are similar to the global climate model output, takes the relationship between a larger scale average, say, temperature and a local observation of temperature, and assumes that that relationship is constant in time, stationary. It will then find 30 observed days that best match that model day in a box around that observation region, and then scale those, or scale the best day of that set of 30 days so that the amplitude in the historical matches the model day, and then it repeats that for all days and all points in the model. And so essentially, you come up with a map that starts off with observed precipitation. You find the best analog days, and so you end up with this kind of tessellation of regions that are behaving similarly to one another, and you apply those relationships to downscale the precipitation. So this pre-downscaling picture would have looked like the blocky figure over something, well, maybe not even that, something like this, and then it's able to turn it into something that looks much more like the observed precipitation, reducing the error. And one additional step that has been done is paring down the number of options. If we started showing you 32 different models, and I showed you the projection from every one of those 32 models for 15 different topics that we think are interesting, you'll be here until next Tuesday, and we don't want to do that. We also know that not all 32 models are going to do a good job necessarily in California. And so what Dave Pierce did was performed an additional analysis to select only models that reasonably both represented global climate and regional California climate in particular. And there's actually two steps in here. They took it from 32 down to 10, and then from the 10, which still would be a lot if we wanted to show you 10 different plots from 10 different models, that's going to take a long time because I'll show you different time periods and so on. I don't want to show you 100 pictures, maybe just 25. And so they took an additional step to take it down to 4 models. And so we're going to show the best 4 models, which are also picked to represent a warm and dry, kind of worst case scenario, a cold and wet, maybe a better case scenario, unless extreme precipitation is of particular concern. And model that represents the average of all of the best 10 models, and a model that captures the most variability of those 10 models. And this whole process was done through selection of different metrics that were given weights and weighting them and picking them and kind of moving along this curve to figure out which models are the best. And in the Dave Pierce white paper, which there's a link to in the presentation, you can read all his text on exactly how they did it. And it's a really nice, approachable way to understand what's going on. Okay, so some examples of the projections. We'll show the 4 best California models for our business as usual scenario, which is the representative concentration pathway 8.5. There's also a 4.5 you may have heard of. That's considered the mitigation scenario. I don't show those because I'd rather show kind of the worst case output. There are big differences between the two. They really don't start occurring until the mid-century, and I think that's good motivation to push for climate change mitigation strategies, because if we can make a big difference in our late century outcome. That figure Nina showed with Sierra Nevada snowpack declining on the order of 64% based on the RCP 8.5. Under the 4.5 scenario, those changes are only on the order of 20 to 30%. That's a pretty substantial difference. For the purposes of the planning horizon, which I think is in the IRWIM, the next 20 or so years are considered the near future. We'll also show the mid-century and the late century. And kind of a personal remark from my experience in this topic is that late century projections probably could happen sooner than anticipated. We don't like seeing that, but we kind of see that over and over again when you say, well, the coral reef should be good for another 50 years, and they collapse next year. That's not good. So it's really not very bad things. And so I kind of like to sort of let's focus on the late century. Let's assume that's going to happen next year or in the next 10 years. And then when it doesn't happen, you're fine. And when it does happen, you're better off than you would have been. So that's just a little side note there. So annual precipitation varies substantially between models and time periods, and most actually project an increase in the annual average, as Nina showed. And so if we look at the near future, we can actually see several of them are a bit wetter. So the green colors here are in percent difference. The browns are a decrease, greens are browns are a decrease, greens are an increase. So we have Ventura County. The dot just shows where we are right there today. The gray lines are terrain shown at approximately 1,000-foot intervals, just to kind of give you a way to orient yourself a little bit there. And of course, we can add in roads or rivers or watershed boundaries or whatever's more useful for you for zooming in on areas of particular interest. So between the 4 best models, we see one is substantially a bit wetter for this period, one doesn't have a lot of change, and 2 have a little bit of increases. Moving into the mid-century, we see some pretty substantial discrepancy between the models. One is very, very wet, one is a bit wetter, and 2 are substantially drier. Into the late century, there's the late century. Again, we see our wet model is quite a bit wetter. We see a substantially drier model. We see a model that projects some amount of wetting in the bulk of Ventura County and drying further inland, and then another wet model. And as we know, and as Nina mentioned, the precipitation projections are they're leaning towards a bit wetter, and there is a lot of spread between the different models. But we can actually dive a little bit deeper into this and start to understand how this may sort of manifest itself. So if we start calculating things like the change in the annual average number of dry, or where we do not see precipitation days, which Suraj Pallade showed that dry day warming is really a key way in which mid-latitude climates are going to change under warming. It's not going to be, the precipitation is so highly variable in many of these regions anyways, it's really the number of dry days which offers less opportunities for storms and more opportunities for evaporative losses of water to take place. And so in dryland places like Southern California that really depend on a few large storms, these dry day changes are quite impactful in terms of less opportunities for precipitation. So in the early near future, we don't really see substantial changes in the number of total dry days. It's on the order of basically less than 10 across all models. As we move into the mid-century, we start to see 3 of the 4 models projecting increases in the number of dry days, pushing the order of 10, with 1 actually showing a few less. That's the wet model. And then at the end of the century, we see the number of dry days is sort of ranging between probably about 8 to 12, and that's consistent across these 3 models. This model, on the other hand, the wetter outcome, shows a decrease in the number of dry days, and that was also the model that showed the largest increases in average precipitation. And so probably the best way to interpret it is you would take, this one, which is kind of our worst case outcome, and say, how would 10 or 12 more days of no precipitation matter to you? Because that's kind of our worst case outcome. And then you could take the flip of that and say, well, if we had 10 extra days of precipitation, probably some of those are very big precipitation events and may drive increased flood hazard in that outcome. So if we think about the wettest days, we know, based on some work that Mike Dettinger has very nicely shown, that the contribution of the wettest 5% of days to the annual precipitation really drives the variability in California, and that work was also highlighted by Nina's recent paper for the Lake Cachuma watershed, or Santa Ynez River watershed. And if we look at monthly mean contributions to total precipitation, you can see the wettest 5% of days account for on the order of about 40% of our total precipitation, where all the other days in green here account for the other 60 or so percent. But when you look at the variance of contributions to total precipitation, about 80% of the variance is driven by those days, and that is really saying that if we get a few big storms, we have a wet year. If we don't get those big storms, we have a dry year. So the variance is strongly tied to the large storms. And if we start looking, we can do a calculation of the percent change of the contribution of the wettest 5% of days to annual precipitation for the near future. So green indicates an increase in the contribution of the wettest 5% of days. And we see across the board, all 4 models are indicating for the near future an increase in the wettest 5% of days in the early part of the century. In the mid-century, pretty consistent results, still some variability. We don't see as big of a change between these 2 models. And if we move into the late century, this model doesn't quite have as strong of a signal, but we do see changes on the order of 10 to 20% for much of Ventura County, increase in the contribution to total precipitation from those strong days. And that is totally consistent with an increase in atmospheric river frequency and strength. So we have more dry days, less opportunities for precipitation, but when we do get precipitation, more of it is going to come from these big events. And so that has direct implications for flood risk, and probably also considerations for floodplain restoration, managed aquifer recharge, things like that. How can you better store and capture that water that's coming more frequently as a big event? So let's move then to temperature changes. Now we'll see a lot more consistency. So I can give you that. We know precip is kind of all over the place. Temperature, for better or worse, is going to be much more consistent. The drier future concept, as Nina mentioned, is very strongly, we hear a lot about, the drying of the West. What that is primarily driven by is the evaporative demand of increased temperature. Many of the studies on future drying use metrics like Palmer Drought Severity Index or other drought indices that are very strongly coupled to temperature or evaporative demand equations. And so that's really this ubiquitous increase in temperature is really going to be doing much of the drying. So if we now look at the difference in annual average maximum temperature across all 4 models for the near future, we're looking at changes on the order of a couple degrees Fahrenheit, and this is averaged over the year. And you see, now the models are all in good agreement. That's much nicer when we see things like this, even if it's a bad outcome. Moving into the mid-century, we see a couple models, very similar spatial patterns. You can kind of see how the inland deserts, the Mojave Desert, is warming up a bit more than the coastal regions. You can actually see how it's a little bit cooler right along the coast. That's probably because of the downscaling technique actually being able to better capture marine influences. And moving into the late century, we don't like seeing the color bar max out, but it really kind of shows that across all models, the primary projection is on the order of greater than 8 degrees Fahrenheit of warming. So not a good outcome there, but at least we have good agreement. Let's see. Oh, and sorry, so now we're looking at minimum temperature, and we're going to see very similar patterns between all the models, essentially showing consistent increases in minimum temperature, largely focused initially on the inland deserts and then spreading throughout the region. Those temperature changes are roughly on the same order as the maximum temperatures as well. So if we start thinking about temperature extremes, average temperature is great, and there's a lot we can do with that. Temperature extremes are very important in terms of public health, agriculture, water and energy demand, things like that. And we see in a recent application of trying to understand temperature extremes through California for the California Climate Change Indicators Report, which was just released earlier this year, and I did the section on extreme heat. And what we see is changes in extreme heat days and nights are really focused on the South Coast region, which is of great concern because many people live there. And in our definition, we're going to apply the same definition that was used in that study, and we're looking at the top 2% of maximum and minimum temperatures. So really the hottest extremes for both minimum and maximum temperature. And if we look, and I'm just going to show you the late century, so the worst case outcome of all of this. If we start looking at the difference in, oh, did I go the wrong way? There we go. Average number of July and October days exceeding the 98th percentile of minimum temperature, we see that there are quite a few days on the order of 60 to 80, if not more, where the top 2 percentile historical temperature is going to be observed in Ventura County. So this is another way to start thinking about it's going to get hotter on average, but we're also going to see a much greater frequency of extreme warm temperatures. So minimum temperature is very important for public health reasons in particular, as some of you may be familiar with, because you can have a really hot day, but if it cools off at night, you're able to recover a bit. When it does not cool off at night, and this is a big issue with urban heat island areas where the minimum temperatures continue to rise, you no longer cool off and you sort of accumulate this physiological stress. You also use your air conditioning more, which pumps more heat into the environment and produces a stronger heat island effect, as well as causing more energy demand. Let's see, and then so if we go to an example of a specific calculation, and we think about our very sad event this summer, the July 2018 heat wave, where the temperature, this is the temperature trace for Ojai, and I think it was pushing on the order of about 108 to 110 degrees Fahrenheit, and that came after a relatively kind of normal, somewhat cool period, and there was this abrupt, very, very strong warming that took place, and there was substantial damage to avocado, to lemon. As Brian mentioned, I think the oaks were really struggling as a result of this event. Not a good kind of event to have, but maybe more characteristic of what we'll expect to see in the future. So we can do some calculations based on this. I got in contact with a gentleman from the California avocado grower group, and he provided some papers that had information on calculations that we can do, temperature thresholds that are of interest to avocado growers. One of those begins at about 88 degrees Fahrenheit, and that's where the stomates begin to close on the avocado plant, and that's a physiological response of the plant to try to prevent water loss and prevent bubbles from forming in the xylem tubes, which can block flow of water through the plant and cause death or other damage to the plant. So if we start calculating the change in annual average number of what we would call avocado stress days, so days that exceed 88 Fahrenheit, we see pretty substantial changes. You can see the mountains are being resolved in the model where we don't see those large changes. And what we don't like to see is the Ojai Valley having sort of a little bullseye there where there's going to be a large number of additional days where avocados could be stressed. This is kind of intended as an example plot of something that you can give me a number, we can come up with some calculations for you, and you can say, well, I don't care about 20 or 30 of those days, but once I hit 40, that's where things get really rough. And then so we can actually calculate those types of thresholds. Another impact is that flowering problems begin at about 95 degrees Fahrenheit, and we can repeat the same calculation, calculate the change in the annual average number of avocado flowering problem days for the late century. And again, we see while the mountains are being well resolved, and you can see the deserts are quite hot, nobody is growing avocados here, but I think there's a lot grown right in this area. And so we can see that there are changes on the order of 20 to 50 days of additional days compared to the historical where flowering problems can take place. And that's consistent across the four models. So just some other examples. We could repeat these same calculations for citrus, for strawberries, celery, you name it. We can, and if there's a threshold that you know about or that's been published, we can look at that. I think there's other good applications probably for restoration efforts and planting, such as the oaks of Ojai. So moving on to the next steps, what we want to do is we now have the Andres Prien dataset, that high-resolution dataset of extreme precipitation, and we are going to be able to apply it. So this box here, it kind of shows sort of the climate modeling issue again, where a box this size, it gives you a piece of information, but it's not super useful necessarily. The actual resolution of this product is the same resolution, or very close, it's actually a little finer, so better than the models that we're using. So we're going to be able to look much more closely at changes in extreme precipitation at scales that are going to be more relevant. So we can look at how it changes in the mountains, how it changes in the river plains and the lowlands, and actually get a better understanding of how these changes will manifest themselves across Ventura County. One problem with this data set is that it was a temperature perturbation experiment. So essentially they took some historical period of time and they just warmed up the model by a few degrees and reran it. And that's a great way to do it. However, it doesn't resolve circulation changes that are occurring under a warmer climate at the global scale. So a better approach, but one that's very expensive and would require lots of money to do, would be to actually run a Earth system model that has been warmed up through the process of adding greenhouse gases, seeing how the circulations change, and then downscaling that. They didn't quite do that. That's kind of, again, the next step. So this gives you some answers, but it is limited by the approach that it uses, where it just warms things up. So it doesn't actually say, oh, the storms will get stronger. It's more looking at the precipitation mechanisms and how those change under a warmer climate. So we're going to be examining that, and that's at an hourly time scale, so we'll be able to look at that, compare that with the alert gauge network. Apologies for my alert gauge. This is actually in the adjacent county up on Camino Cielo, so we're borrowing from Santa Barbara County here. Maybe we'll go look at some Ventura County alert gauges sometime soon. We'll do an analysis of subdaily precipitation in Ventura County and use this Prien data set to compare it. We're particularly interested in spatial changes, so are mountains changing in a different way than the lowlands, because that has very substantial impacts not only on ecology, but in particular mass movement and flooding. And then we can also look at some of the seasonal effects as well. Are these changes in extreme precipitation constant throughout the year, or are we going to see different changes in how the characteristics of extreme precipitation that may be relevant to things like pests or having moldy strawberries, which nobody likes. And so we can start to look at those kinds of outcomes. So we're really interested in your information so we can produce output that is useful and relevant for you. So we're here to respond to your specific needs, help address concerns. If you have any types of questions about climate modeling or downscaling or what the future may be, we can provide as best we can information on that. If you think of calculations you'd like us to do, we are happy to do so. And we're working with Lynn and friends on really trying to advise this prioritization process for the IRWIM planning, and so your feedback is really welcome there as well. And then in terms of your larger planning that may not be IRWIM specific, we can help kind of address issues of planning amidst the model uncertainty, being able to interpret how to deal with that a little bit better. Any input, insight, discussion is always welcome. Our email addresses are here. I think Lynn also sent them out. Please get in contact with us, and I'll just leave you with a couple of the concluding remarks. So, thank you.
We're going to take a 15-minute break at this time, and so before we send you off for break, while you are out mingling with your colleagues, consider some of the information that we've just presented and what are interpretations of it, what are concerns for your particular group, what kind of thresholds would you like to see, what time periods are important, what are your concerns with these data and the uncertainty associated with them, and any other analyses that may be interesting to you. And when we come back in, we'll have a group discussion on that.
Thank you, Nina and Ben, and let you go to your break, but I just really want to encourage everybody to stick around for I know it's tempting to go back to your day, but this is a really important part of the discussion coming up after the break, is to take all this great information, highly technical, but really important current data about climate that's going to help us better adapt as we move forward in not only preparation of our Integrated Regional Water Management Plan amendment, but also the County General Plan update, which is ongoing now, development of groundwater sustainability plans, which are happening across the county. This is really, really important information for all of us to use. And not only do we want to make the state happy with our IRWM plan, so that we can get money for Prop 1, we all need to be engaged in this dialogue and working together to figure out what are the appropriate strategies for us to be implementing locally, and how do we assess our vulnerabilities. And, we've got the experts right here to help us. So I really want to thank both of you for your presentations and look forward to the discussion that we have after the break. Please come back. And we will try to get out of here. We said 12:30 as the outside limit for this day. I don't know that we need that much time. I know you're going to probably want to hit the road when it's lunchtime, so we'll do our best to be out of here by noon. And as a reminder, if you have trouble focusing on everything other people are saying because you're thinking about what you're going to say, you're going to have the recording later to go back and hear the discussion. And I think that's going to be a really important tool for all of us, because I know for me, absorbing that kind of information it's a little challenging. Some of it's new, and it's our job to collectively try to make sense of it all and move forward with our planning efforts. So thank you again for your presentation, and we'll have some great dialogue. We'll come back here no later than 11:15. So thank you, everyone. Yeah, where do you want that?
Bring it up on the stage.
Okay. Got it?
Yeah, it'll help to write some.
So we have two mics, one for you guys and then one that will circulate in the audience. So here's yours.
Thank you.
Do we want to turn the computer off or just leave it?
Let's leave it up there because in case we put a pretty picture up. And because then if we want to go back to any slides.
Somebody-
that seat right there, and someone
dropped
left
their
these keys.
Maybe they just left for briefly and they're coming back.
I would think so, but I haven't
Oh,
seen
thank
them
you.
around. I think they were wearing a purple shirt.
Okay. I didn't notice who that was. So.
Yeah, I didn't either.
We'll put 'em
They
up
can't
here.
get too.
They won't get too far,
It's
yeah.
a Mini Cooper, so we'll go find it.
Okay.
Try to find it.
That the deadline for entering,
Your project-
pre-application is Friday. Is that right? Yeah. So we submitted one for.
I saw that, yeah.
But we have one for this one, Kairu
Okay.
area. It's a disadvantaged area. So
Great.
okay, Friday.
Yeah, Friday. Yeah. And you'll get a reminder from me probably this afternoon about that. Okay. All right. We really are going to get started. I want to make an announcement about parking. For any of you that are parked out front in the 3-hour parking, reminding you that that's only 3-hour parking, which is the one, if you're facing the admin building, it's kind of the public lot just closest to the building on the left. And they do ticket. So if you're walking out of the building, it's on your right. It's the lot closest to the building. And on the left, you're fine, right? And if you're on the side with the solar panels, you're fine there too. So it's just that narrow sort of band of parking spaces to the right of the building as you're exiting. So just want to remind people, don't want any tickets. Also, we found a set of keys on a chair. And does anybody know who that was? Is it a Beamer? It's a Mini Cooper. So I'm going to put them up here in case nobody's going to claim them. Okay, so we have an extra mic here and we do need people to speak into the microphone in order to capture what you're saying. So I'll be running around handing out the mic to folks that have questions, and please wait until the microphone comes before you start talking. So go ahead, Nina and Ben.
All right. Great. So I'm going to try and log some of these on some of the discussion pieces or any recommended thresholds that anyone has on the whiteboard here, so we can see how we're moving along. And we're also, I think, many of us will be taking some notes as well. But I guess we'll just start off by opening it up for any questions, comments, concerns, or thresholds or things of interest that folks would like us to look at. So Lynn will be choosing who gets to start there.
So I was really glad to see the slide up there on Santa Ana wind events. And first of all, I was wondering, I didn't see on there the 35 to 40% type decrease in wind events. Was that over till end of century? And I was also wondering, what is that a function of? Like, what do you think is affecting that? Is it land surface temperatures or what?
Yeah, so I believe in would definitely have to double check, and so I'll put it in the version that we put online. But that is a late century change. Is that the late century? Yes. So it is the 2070 to 2099, and the decrease in the Santa Ana winds is meant to be related to a decrease in the pressure gradient between the inland area, the Great Basin area, and the coast. And Ben's worked on Santa Ana winds a lot more than I have, so do you want to add anything to that? Yeah, so it's a function of the decrease in the pressure gradient. As air flows from the high pressure inland to the lower pressure, you have acceleration of the winds. He might be drawing a picture. Yeah, and so Lynn's gonna get it.
My name's Ron Mercord, and I'm with the Santa Clara River Conservancy.
Okay, Ben's going to draw a little picture here. But basically, the driver of the Santa Ana winds is the pressure gradient from inland to offshore. And if you weaken that pressure gradient, you also weaken the strength of the winds.
Yeah. Okay. So when we have a Santa Ana wind event, like we have,
on a topic of interest.
yeah. Typically, what's happening in that event is you have a strong area of high pressure over the inland region and some sort of low pressure offshore, and you have this very strong pressure gradient. Air wants to flow from high to low. And as a result of and this often coincides with a large area of cold air at the surface. And as we warm the land surface temperature and we reduce the magnitude of this cold air, that coincides with a reduction in the high pressure, which will reduce this temperature gradient and subsequently result in a weakening of the Santa Ana winds in a climatological sense. It doesn't preclude an extreme cold air surge from the Arctic, and that often coincides with so our upper level pressures start to look kind of like this. We call it a breaking
Situation right now.
Rossby wave, where you actually have an upper level low, a surface high, and this is our big high pressure ridge that's taking place. And when you look at a map of this, and you'll see these lines, wind blows parallel in a general sense to the isobars or isoheights, and you get flow at the upper levels kind of moving in the same direction. So you have at all scales, you have this inland to coast flow taking place. We can still have all of these things take place under a warming climate. So I'm guessing, having not read Hanin's paper on it specifically, that as we warm up the land surface region, you're going to reduce the likelihood and magnitude of these cold air pools, and also probably weak the upper level wave process that's taking place that collectively are driving our offshore Santa Ana winds that make stupid fires blow off over the coast. So, great question.
I probably won't do as well. Anyway, Bill Warwick, City of Ojai. I have an atmospheric river question. You've talked about the change predicted pattern for atmospheric rivers hitting Southern California, basically where we are now, or southern or central. California is a very long state with a lot of different latitudes. So when are these atmospheric rivers that, in terms of the range of latitudes that we have here in California, will those be probability linked or correlated in probability at all, or completely independent? In other words, is an incidence of atmospheric river and that pattern occurring in Southern California, is that completely diverse in terms of probabilities for central and north? Or when one occurs and the conditions occur in Southern California, is that going to be linked to the probabilities occurring in the other watersheds in Central and Northern California?
Do you want to answer, or do you want me to?
Yeah, you can add on to what I give. So some of the studies that I was showing here, I'm trying to focus on Southern California, but are generally West Coast oriented, and so we do expect the changes that I talked about in atmospheric rivers to be along the length of California. And additionally, there's a study that I cited by Espinoza, 2018. I'll give all the links to the papers if folks want to dig in deeper. But what she noticed in her study of, I think it was the Espinoza paper, correct me if I'm wrong, but a slight shift, southerly shift in an area of atmospheric river frequency, such that you see an increase in frequency of atmospheric river conditions moving into Southern California a bit. Do you want to add anything?
Yeah, and I think if I'm understanding your question right, so we do have different atmospheric river kind of favored regimes. So if you sort of like the video that Nina showed, you could kind of see how there's sort of different flavors of atmospheric rivers. There's kind of the one that I sort of think of it as like a fire hose kind of spraying down the whole western coast of North America. But then if you do and then there's other ones that are kind of like the classic Pineapple Express, where it's just sort of this 45-degree angle coming into somewhere. If you do some clustering type analyses, you do see different regimes of atmospheric rivers and how much of the total number of atmospheric rivers for the whole kind of Northeast Pacific are related to those different regimes. And I don't think Vicky's study looked into that, because hers was much more of a global study. But I think Sasha Grishunov at Scripps actually are working on they have a new paper, I think in review, where they're looking at changes in some of these different specific atmospheric river regimes. So we could look, there is one that shows up for Southern California really nicely, and that would be a specific one that we could get their information and look at to see how atmospheric rivers change for that regime, because that's the most applicable one for direct impacts to the region.
Hi, I'm Mary Bergen, Casitas Municipal Water District. In the last couple of years, our lows have been going straight north-south or even inland rather than coming out over the ocean, which is where we get our good rains. Could you explain about that, and please tell me when that's going to stop?
I haven't been paying as much attention as Nina, so we'll get her.
Yeah, I can try, and I actually did hear this same question from Santa Barbara County. As you know, I went down to, as I was starting my studies, I went down to talk to them about what's interesting to you guys. I've got some time. I want to study Southern California. What can I do? And they said, well, when are the storms going to start coming here? And it's really tough to figure out why the troughs haven't dipped down in the same way. I guess the answer is that I don't have a great answer. We have been in a regime where ridging has dominated, high pressure has dominated over the West Coast throughout the whole drought period. But there's been people who have pointed out, well, the storms are kind of skipping Santa Barbara and Ventura County in particular. So I don't have a great answer. It's something that we can certainly study. I don't know if within this project, but it's just due to the particular pattern going on. Don't have a great answer, unfortunately.
Hi, I'm Jamie Jackson with California Department of Fish and Wildlife. I noticed, Nina, I think that your data ran through 2017 for your precipitation predictability models, and Ben, yours was through 2016? Perhaps the data that you were looking at?
So I showed an example of a study we did for Santa Barbara County using historic data, or for the San Ynez River watershed, that went through from water year 1966 through 2017. And then everything we were showing after that was future climate model projections. So that was actually based on observed weather station data.
Okay, so I have a question about the observed weather data. So since you had mentioned that the rainfall predictability models are somewhat less
in agreement.
Yeah. I'm just wondering, did you guys use your models to try to predict, say, 2018's rainfall to see what the accuracy might look like, with very near data, to maybe strengthen the projections into the near future, the 2039 data? So if you did predict 2018, has it been accurate?
So we had looked at observed data, these climate models, and we have, of the 32, we're really focusing in on the 4. We don't tend to use climate models to look at these large-scale climate models to look at individual years. They don't do great for making a prediction of individual years. And in fact, one particular climate model may be very dry for 2018, and one may be very wet. There's a lot of spread, but what we really use them for is to look at changes on at the least period of time I'd look at is decadal, and then you usually want to look at multi-decadal averages to understand how the presence of how the temperature changes on average and how the precipitation changes on average. You'd be down to what are called seasonal outlooks, seasonal forecasting for the near term, for looking at a particular year. Do you want to talk anything about S2S or outlooks? Yeah.
And so one thing that that's kind of out of the scope of this project, but looking at the year-to-year forecast, so we do have models that are basically global climate models. They're just finer resolution and tend to do a little bit better for various reasons for the 1 year or several month forecast. When we have a year like 2018 where it just doesn't rain for ages and ages, and maybe it doesn't really rain much at all, we can still gain information as far as how the models, which ones are doing a good job capturing those kinds of events, if they have one of those in their 50-year historical run, or if they don't have any. And if they don't have any, we know that model's not getting something right that's really important. And so, although we're not focused on that here, and it usually takes a couple years for people like the great El Nino bust of 2015-16, now we're getting a better understanding of, why did all our forecasts not pan out that year? And it turned out it was we are misrepresenting sea surface temperatures in a part of the Pacific that we previously had not thought to be as important, and that kind of highlights areas for models to improve. But the time scale that improvement takes place is a couple to 5 year sort of process. But then with these models, what we're really looking at is just, are they in a statistical sense? So we're taking a bunch of output from different models and seeing, are they in agreement, are they in disagreement, what kinds of magnitudes of changes, but then individually, are they getting the right process or not? Part of that actually comes in with that taking the 32 and going down to 10 and then down to 4, because if models are not getting things correct that we know are very important, those get tossed out. And then if they're not getting California-specific aspects correct, those get tossed out. And then that's how we kind of move down.
So then will your next major accuracy period be to look at the 2020 data then and see if the models accurately predicted that?
I think I guess the only problem then is we have to wait until that takes place. But there is a pretty substantial modeling community who's really interested in kind of looking at the last 10 years and seeing how well the models did for that most recent period, where are the weaknesses, and then there's a pretty large group that convenes, I think it's every year, every couple of years, to say, what are our big next steps in improving models? And I know the sea surface temperatures, and specifically the gradients of sea surface temperatures, so how much sea surface temperature changes over a distance. If you're where the upwelling is, it's much colder, and you move 20 miles offshore, it gets much warmer. If we don't represent that very well, that can have a big impact on the model's ability to correctly represent the physics. And so there is a big group working on that, but I think at the time scale of this process and planning, Nina and I won't be able to quite address that.
Yeah, and there is a lot of work going on. It's called in the climate meteorology community S2S, which is seasonal to subseasonal. So there's a lot of work right now on looking at, can we improve seasonal and subseasonal forecasting. But the work that we're doing right here is more for climate adaptation planning. So whereas in the S2S community, when you're looking at how well are we doing for the next 3 months or so, then you would go back at the end of those 3 months and say, okay, our model failed here, here, and here. Why did it fail? Okay, now moving on to the next season. So different types of models, different types of outlooks and timescales associated with that. And so we're focused more on this long-term climate adaptation planning horizon in this particular study. But we can certainly help direct people to S2S subseasonal resources if desired.
You're going to have reliable data feeding into them over the long term. So if the short-term data isn't reliable, how can you possibly say that this long-term data is going to be reliable? That was my question.
I think as far as the global model reliability, we're pretty confident that even though they can still have some specific errors, but if they're getting the signal correct, in a general sense, we know that they're still useful, because we can say, well, they miss a few things here and there, and that's why we tend to look at not just one realization of one model. And a lot of these models, they'll run them 50 different times, changing things just a little bit, and so we can kind of get a good handle on the uncertainty within the models. But we know that if they're doing a reasonable job, they're our best tool, and we can still change things in the model, like greenhouse gas concentrations, to see what an expected output may be. And so that's kind of the bridge between weather and climate modeling, is that if the weather model's messing it up, we want to really fix it. Whereas the climate model, we know there's so much uncertainty and so many problems that are inherent in them. If they're getting presenting a reasonable picture, modeling, that's kind of the thing. It's like, is it reasonable or not? That's the debate. It's not whether the model's right or wrong. The models are pretty much always wrong, but are they reasonable? And the broad consensus is the models, for the most part, are extremely reasonable. And there's been some recent work showing that the most reasonable models are the ones that do the best representation of clouds. We know clouds are very important. And the ones that do the best job in the historical period have the best representation of clouds. And the kind of scary aspect is those are also the ones that predict or project the most dire outcomes, which is not good, but it gives us a way to put more weight into those models.
Yeah, and we are here to help you folks understand the uncertainty within the models too, and which there certainly is, especially with precipitation, as we've discussed. So we encourage questions on that and to know how it impacts your planning.
Hi, I'm Karen Bosson. I'm an executive director of the crew and a board member of Ojai Trees. And I wondered if you might be able to do a calculation, such as you did about the avocado trees and the upper reaches of temperature beyond which they won't be viable, if you might be able to do that for the oak trees of Ojai. Like, at what point does the temperature become too high for oak trees to become viable, so that we might know, if they aren't going to be viable, what tree species we should be planting?
Yeah, certainly. And really all we need is basically a number of concern, which could come from a oak tree specialist or based on anecdotal information that you guys have seen. And so if you can provide us with a number or a range or some information to do the calculation off of, we have, all the information that we showed, it's daily temperature, so minimum and maximum temperature, and daily precipitation. And the Preen data set is hourly precipitation. I think it has temperature in there as well, although I wouldn't, it's not really set up to do future temperature, hourly temperature calculations. There are other statistically downscaled products that are at sub-hourly timescales, and so we could use those if there's information, the diurnal temperature range, so the difference between the minimum and the maximum is important, but so too is the duration within that 24-hour time period that a temperature may be important. And so we could certainly look into the availability of that kind of information, but if there's a number, like a threshold maximum temperature above 106, and then 80% of oak trees cannot recruit or die, we can definitely do those kinds of calculations for you.
Hi there. My name's Candice Manigan. I'm with Friends of the Santa Clara River, but I also sit on the board for Fulmar and Pirate Basin's Groundwater Sustainability Agency. And I just recently attended the first Western Groundwater Conference up in Sacramento and got to sit in on their data session. And there was a lot of talk about models, and it's about what data you put into the model to get what you get out of the model. And I think the biggest concern was, one of your slides was like, a lot of our precipitation is on these big events, and they're quite rare. And what we're going to have to do with the GSP planning is looking at that historical data, and it's a very stakeholder-driven process. So the stakeholders actually get to choose, what the historical data set is going to be. Are you going to do 20 years? Are you going to do 100 years? And one of your comments was, if you miss one event, it can actually skew stuff quite considerably. And so how do we, especially with the precipitation data that is some of the models are so contrary, how do we plan? Is there guidance on how you select your historical data so that you are not introducing that room for error, so that you're actually getting outputs that are, more reliable for your planning? Because, when I saw those contrary models with very wet and very dry, I'm like, well, how the heck do you plan for that? And, I think the concern for me especially is we are Ventura and Santa Barbara County not getting the rainfall. These are precipitation-based basins, and it's going to be a challenge to balance, environmental and farming and community needs. So we really do need to be making informed decisions with informed data, and right now the data is very contrary, and that's worrisome.
Yeah, so for historic precipitation data, luckily Ventura and Santa Barbara counties actually have very good precipitation networks. It's part of their flood control network that has kind of evolved over time into being stations that you can use as climate stations. And so there are a number of stations that are part of the National Weather Service Cooperative Observer Network that have fairly good records in the area, but Ventura County Watershed Protection District maintains a network of gauges in Santa Barbara, or in Ventura County, and then Santa Barbara County Public Works Department maintains a network of gauges, and those, I know I've worked more closely with Santa Barbara's data, and those go back at least to the 1950s and some before. So as far as getting your hands on historic data that can give you a good representation of the big events and variability, those data are there. If you're looking for spatial data, there are some data sets such as the PRISM data set, which struggles with individual day extremes sometimes, but we kind of try to use weather station data whenever possible. And then if we really need that spatially averaged, we'll use these data sets like PRISM. And I can point you to I'll give you my card and point you to some particular data sets. Now, whether climate models are capturing all those events is a different story. So so how to see, what the models are doing historically, if they're getting that and looking into the future, it can be a challenge. But if you just need to get your hands on historic data and see what that variability has been, and then we can see Ben showed some of those changes in extreme storms in the future.
Okay, hold on. Want to finish this. Did you get your question answered?
Just a follow-up.
Yeah.
So they actually ran several models, and one of the things that came out was, it didn't pick up all the events, and so how do you select so that it is to remove the error, or basically?
Do you have any?
Because what happened was, I think it was for Fox Canyon actually that the example that they used was for Fox Canyon, which is here in Ventura County, and so it's like if you're not getting I think they wanted to use 100 years worth of data, but the stakeholder process was like, no, we're just going to use this amount. We don't need to go, so far back in the historical record, and then it missed some of the information. And so I think that's where it's also tough being a stakeholder-driven process. And I think that's where I think we could use some help on guidance, is so that we are using, we're selecting the historical data correctly, so that we're getting accurate outputs. And I recognize that it's a stakeholder process, but it's also like you are the experts, so can you provide guidance on how you actually select the data for your modeling?
Yes, and certainly, and it would be helpful also to get more information on what they're doing with the models and how they're feeding the data in. So, yeah, so we can get our contact information to you.
That'll be the subject of a focused conversation tomorrow at 1:00 with the GSAs in the area that are able to attend. And I know Candace is not able to attend that meeting, so I think we have record of your question. I think we can kind of continue that conversation and record that, because that is a whole area of planning that we're trying to help with the information that we're providing through what you're doing. So,
and I think, Candace, you point out a number of issues. Climate models provide projections. They're not weather forecasts, right? So it's kind of like the lady in the back said, tomorrow Weather Service tells you that it's going to be 70 degrees and sunny. You can kind of think back, okay, was it accurate? With projections, it really shows a bit more on really the trend and the direction. That having been kind of a climate geek, you kind of know, kind of like you said, the information that goes into a model needs to be good, or else it'll still be garbage. If you put garbage data in, garbage output comes out, right? And I think the reason why we chose 4 different models is to give you the different scenarios, basically the ranges of possible outcomes for what we might see. And so I think in the past, when I've participated in climate adaptation efforts, which is what GSAs are really doing at this point, is number 1, make sure you're putting the best data and information into your models. Number 2, in an era where we have unlimited resources and money to combat climate issues, we would of course try to adapt to the worst case scenario. I think what we are going to see is that we don't have the unlimited funding and bandwidth to respond to the worst. So then what can we straight face say, well, we're gonna try for the second worst scenario, and these are the things that we need to do to adapt to it. I think it becomes a decision as a community and as a society on what are we choosing to adapt to based on what we know the worst case scenario might be. And I think that's kind of where we're going. It's not about, coming up with the 100% scenario. It's coming up with what are the ranges of possible outcomes and then deciding on which to respond to.
So Charles Lester with the Santa Clara River Conservancy and UCSB. And as a follow-up to that, I've worked quite a bit in sea level rise and adaptation planning along the coast. And so similar evolution of using models of projecting what sea level rise is going to be in different scenarios or time periods, near term, mid-term, long-term, similar to your time periods. But the most recent iteration at the state level made a move towards probabilities in characterizing those outcomes. And in land use planning and adaptation planning, which is not so much what's going to happen next week or forecasting, but how do we plan the use of this area over time, it's really more about risk and the probability of certain things happening or not. And so I guess a 2-part question. One is, are you moving in that direction also in terms of not just looking to different models and how they may project outcomes or projections over time, but rather the probabilities of certain ranges of outcomes in those periods? And I say it that way because one of the other things that's going on in sea level rise planning is that communities and people tend to see a date and they go, oh, so it's going to rain that much in that year, as opposed to a likelihood of a certain amount of an increase in an event or a frequency of the event, the size of an event, out here somewhere. And it may be sooner, it may be later. Are you moving in that direction with your work? And then the follow-up, based on where you are with your work in Ventura County, what's the takeaway today in terms of how we would characterize the likelihood, and let's just take precipitation as it relates to flood concerns. Is the statement from the best professional scientists, it's highly likely that we're going to see increased magnitudes of rain events that will lead to flooding in the next 50 years? Or just how would you summarize that?
Yeah, so for the first question, I think the problem with the 4 models is you have a small sample size, so it's harder to say, well, 75% agree, and that's where we would go to the 10 models or maybe even the 32, and then one thing you can do is you can make the exact same plot and you can say, I'm going to put crosshatches over all the grid cells where at least 80% of the models agree that this will happen. Or we can start calculating odds of a given year with more than 10 days above 95 degrees. So I think that's definitely a direction we certainly can go, and if that's helpful for the wider group, then that's certainly a direction that we will go, and because it's really only just a few extra calculations. But I think, and a lot of climate model projection papers now are kind of using that metric of here's the changes, maybe the average changes, and then instead of calculating a statistical significance, they're calculating where 80% or 75% of the models agree on at least some threshold of change. And so I think that's a good method to kind of get across the idea of probabilities. Or you could make the same plot where you'd say, out of the models, the 50% or the 75% or the 95% probability of a given threshold is going to take place over these regions. And then the second question, which I may need a quick refresher on, the flooding.
What do you think's going to happen?
Yeah, and I think the flooding question, I think, is a really good example of how we saw with the average precipitation, it's kind of all over the place. But then when we look at the contribution to annual precipitation from the most extreme days, and all the models are suggesting that a larger contribution of our annual precipitation will come from the wettest 5% of days, to me, that suggests that the much more likely outcome is going to be we will have more flood type events in going forward into the future. For an average year, we may not know necessarily or be nearly as confident that it'll be a wetter or a drier future, but if we start seeing that all the models are very consistent and the dynamical change or the circulation changes are also pointing towards stronger events that we know today produce flooding, if the suggestion is more of those kinds of events and more events that are contributing a larger fraction of our annual precipitation, to me, both of those indicate that flooding will very, very likely be a continuous and growing concern, and is probably going to be a likely outcome.
Yeah, and to kind of add on to that, I think to not ignore the fact that we also have increased risk of flood. We also have increased risk of drought. So we may see more years with these big storm events, or we may see a relatively dry year that's punctuated by one large storm event. And this can be, what I've seen in popular media, this can be really confusing to people that we're in the middle of a drought. Why are we preparing for flood? Why are you telling me to be concerned with flood in the middle of this persistent drought? And so trying to communicate that message is really important as well, that yes, we're at greater risk for drought. We may have these increased dry periods, but they still will be we anticipate as the climate changes, these dry periods will be punctuated by these larger magnitude storms.
And I appreciate that question, Charles, because I think the probability issue and the risk issue is important for us to be able to capture in our planning effort. And this is why we have all of you here today, is so that we can help drive the next steps in this process that Nina and Ben are helping guide us with. So appreciate that.
Hi, I'm Susan Pan with the County and Ventura Water and Sanitation Department, and I just kind of want to follow up and then add to that your comment. I think it is part of what we do when we do our projects, that we really keep that in mind to try to capture when we have the big flood, big storm, because we do have projects to divert stormwater to, for groundwater recharge, all kind of beneficial use. And so while the opportunity is there that we can capture it and to, store it for the, droughts, for, the days that we actually need that. And I think perhaps that, with all these studies that we should need to also somehow kind of become increasing our design criteria, because the floods are getting bigger, and then if we are designing our facilities to a 10-year storm event, I'm looking at Peter Shade, who's our design department manager. So these criteria, I think, needs to be elevated, because you need to be protecting your 10-year frequency event is going to be a bigger flood than what it is now. So some of these perhaps needs to be translated into the Skylines criteria that we're using. And the same thing, I know you mentioned you have many different models. But the same thing leading back to what Candace was saying, that I know for the groundwater sustainability plan, the groundwater modeling, that they are using currently 35 years of historical data. But still, even projecting forward, that I think, I'm not totally sure, but I think the state already has indicated that they need to adjust it for the near-term future and long-term future. I don't know if you can comment on that, based on whatever the available data and forecast data they have to make guideline to establish some kind of guideline that what kind of increment, what kind of adjustment they need to make in the groundwater modeling program for forecasting the future.
Yeah, I know that there's been some, because currently I think what most when engineering is done for floodplain management, it's based off the NOAA Atlas 14 return intervals, and there have been some rumblings about and some talk about moving towards, well, how valid is NOAA Atlas 14 going forward? I can't remember what year it was last done, 2007 for the, I want to say for the California area. And so there's starting to be talk of how valid is that, how much can we count on that for our planning. It would be helpful for this particular exercise to get some of those thresholds from your group. So, how many inches in a day or persistence of like a 3-day precipitation total of X is when we do Y. And so getting some specific numbers we can look at would be extremely helpful, and we can run a few plots and look at what's going on. In terms of groundwater modeling, out of my area of expertise, you have a little bit, but I think there's definitely some thought towards how valid are these average recurrence intervals that we're currently using going into the future. No one's quite attacked it yet. I know we have a meeting coming up in March, the Southern California Extreme Precipitation Symposium, and and I was asked to talk about actually just that, is in a changing climate, or even in the last 10 years, are those thresholds, are the NOAA Atlas 14 values still valid? Do we need to think beyond that? So there is momentum going in that direction, but I don't have an answer right now.
My name's Russ Baggerly with Casitas Municipal Water District and the Ojai Basin Groundwater Management Agency. Can your models tell us why the ridiculously resilient ridge forms off our coast in a high pressure zone and drives all the storms north?
So that's pretty much a very active area of research, and we saw that the RRR essentially sat there for 5 years and caused all kinds of headaches. But then we know from the paleoclimate record, and if you spend time, especially in the Eastern Sierra, like Mono Lake, Tenaya Lake, or the Walker River Canyon, we have very stark evidence of droughts that persisted for much, much longer, where there's tree stumps that are sitting in the middle of the Walker River and poking out of Mono Lake and poking out of Tenaya Lake. And when you date those, they correspond to a period of time known as the medieval climate anomaly. And some of our work has estimated precipitation reductions during this medieval climate anomaly, and they're essentially the same as what we saw during the 5 years of RRR, but then when you count up the number of tree rings, indicating how long these pretty large Jeffrey pines grew in what once was a river and is now again a river, we see that those droughts, there were 2 of them, and they each lasted for, the first one was about 200 to 240 years of 60% of average precipitation, and then the other one was about 140 years. And so that brings up the interesting question of, so if we had this for 5 years, what would happen if it lasted for 100 years or 200 years? That would be very bad. And then the more climate modeling type question of why does that occur? And we have a colleague, Sloan Coates, who did his PhD at Columbia, Lamont Doherty Earth Observatory, on that exact problem, and his answer wasn't particularly enlightening. It was internal variability of the climate system that drove the establishment. It wasn't persistent La Nina temperature or SSTs, it wasn't this, that, or the other thing. It was you have this complex system that can kind of fall into these stable modes where the ridge establishes, and because the ridge is there, it sort of facilitates the persistence of other processes that kind of help reinforce it. But I think that addressing that question is extremely important, because we can start thinking about, well, what are the likelihoods of more RRR conditions? Some of John Chang's work has shown that the loss of Arctic sea ice is very important in driving the Okay, then driving the establishment of the subtropical Pacific High. This last year, 2018, we saw one of the largest amplitude Madden-Julian oscillations on record for a given location. So that's the tropical convection and the, I guess at this point, or at the location that it was extremely strong convection thunderstorms in the tropical, I think it's the maritime continent, so around Australia, in that neck of the woods. I could be wrong on that, but essentially very, 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 very strong convection, and the teleconnection of that was to drive this persistent ridge that basically sat over us for almost 3 months, and we got no rain in Southern California, which kind of led to Thomas Fire and other situations developing as a result of 2 of those kinds of events. And so we know that sea surface temperatures may not explain it. Arctic ice probably has some, essentially everything probably has some role in it, and we can't point to one thing or the other, and we have to start doing these long global model simulations to start getting at what combination of events are driving this. If they occur kind of out of natural variability, that means it could happen under any conditions. And then we can start looking at what are the likelihoods of those sets of combinations where we have the Madden-Julian oscillation and its favored position for strong ridging off the coast of Western North America, when the SSTs are also in favor of that, when the Arctic sea ice, what's left of it, is driving that. So I think that's a really active area of research, and it is nice that with these models we can look at the precipitation and temperature outputs of the downscaled models, but then we can also look at the actual model output of, say, 500 millibar heights, which is how we typically identify ridges and troughs in the atmosphere, and we can look at, do these dry periods coincide with really persistent high pressure systems, or is it that the storms in that year are just a bit weaker? And we can start to ask and answer those kinds of questions, which I don't think necessarily we're doing here, but is, yes.
Just for comfort's sake, basically. I have a quick follow-up question for comfort. When you were talking about the paleoclimate record showing the 100-year drought and even 200-year drought, there were drops of rain, right?
Yes.
Okay. There were still rainstorms despite long periods of drought. Yes. So it's good. It's a good thing to remind ourselves, because I think I heard gasp in the back of the room.
Yeah. So that's chapter 3 of the dissertation. Chapter 1 was estimating comparing the recent drought with these paleo droughts, because that was the big question. Are we in a mega drought? And we can say, well, this is what a mega drought looks like. That was 5 years. Imagine 20 or 100 or 200. And one of the subsequent follow-ups was, well, we know mega droughts or persistent dry periods are not devoid of interannual precipitation variability. We can still have some rain. And so what's a fun way to address that is we use terminal lakes of the Great Basin as sort of our natural rain gauges, and we can say, when the lake was at a given level during these mega drought periods, it was very low. There was still Mono Lake, there was still Walker Lake, there were still all these lakes, but they were very low. And we can use hydrologic modeling to say, okay, we know that we had to have precipitation anomalies on the order of, say, 60% on average, and that gives us the lake level we want. Now we can start turning the knob and say, well, how many wet years can we have and still keep the lake at that level? And we can see that essentially we can be under megadrought conditions or megadrought-like conditions, and we can have every 10 years we can have one very, very wet year, or we can have 2 to 3 average years, which is kind of scary when you think about if we go back to 2012 and we had 5 years of very dry, we had kind of a wet and another year of dry, and it's like this is starting to look like a 10-year plot that we made. So there's still some interannual variability, and what I think that really should motivate with planning is how can we better capture, store, and use that water when we do get it? Can we come up with, I guess, adaptation measures that will optimize water when we have it, and so that we don't necessarily lose it? We know we have to meet all of these demands of consumptive use, agriculture, urban, keep plants and critters happy, and hopefully not flood the neighborhood. How can we really optimize 5 years of drought punctuated by a wet year? And I think that sets up kind of a good modeling scenario to approach some of these cases. And that's kind of what the model output sort of suggests as well, with more dry days, bigger storms, how are we going to deal with that?
So on the topic of the persistent high pressure, the persistent ridging, one benefit of that, if you want to have a benefit, is that we hypothesize at the seasonal forecasting scale, it may be we may have more skill at predicting the persistence of the ridge than of forecasting the incoming low pressure systems that bring precipitation. And so there's a lot of work right now on looking at, can we use persistent ridging as a forecast rather than focusing on the storms, focusing on the not storm periods. And so that is one way folks are targeting seasonal forecasts.
Hi, I'm Henry Gromlich with Cayugas Watershed and Cayugas Municipal Water District. And first, kudos to WCVC for bringing your expertise to the rest of us. And I guess part of my question is trying to figure out how we can fund more of your work. And part of that is, and I don't want to take a collection right now, but but part of that is figuring out, as you build up this understanding of local impacts on weather. We have a couple kind of siloed and different approaches that have very specific ways in which climate change information is then incorporated into our planning. And so I don't know if you're familiar with the guidance document on climate change data use for groundwater sustainability plan development. But I would recommend that in terms of seeing how that is specifically used for water budgets that then inform the SGMA process, and figuring out then how I think it would be useful as a Ventura County to have just one set of climate experts rather than dozens of them. And then with the IRWIMP planning, I know that we have in the plan, there's a specific identification of vulnerabilities and then understanding how the broad take-homes from climate change scenarios affect those vulnerabilities and prioritization. Do you have, if you could kind of sketch out your plan for how you anticipate having dialogue with those different requirements and how we might better support your work in a way that has kind of this practical application.
Yeah, so I think that's part of what we're doing here today, listening to you folks, and then we're also holding individual meetings with some groups to get feedback so we understand more about what do you do, what are your limitations, what are the thresholds that matter to you, so we can help provide the climate information to support that. So I think it's going to be done very much through dialogue with folks in this room, through follow-up emails, so that we can give the right information. We can't decide what your priorities are. We can advise on it, but we want to hear from you and provide you the information that you folks need to choose those priorities. And you might have.
And just to follow that up, not only is there a guide, as you know, a guidance document for GSP development, there's also a guidance document for IRWM plan development, and we've been sharing that information with Ben and Nina so they would understand, and the websites for the DWR SGMA website and other things, and it's a lot to like digest because there's a lot of information. We're sharing the general plan update, climate information, trying to do our best to pull this all together, and this process is just sort of in the early stages. We have this grant through I think June, and we'll use what we can now in the update to the plan, and it's going to be an ongoing, we'll be able to incorporate, it's a dynamic plan, we can incorporate new information going forward. So absolutely, that's really a critical question, so thank you. I've got people that have been waiting for a question. Is this? Sure.
I think we're collecting as much questions as possible. I think it's just really a good expectation setter that this is kind of to me, a first baseline study that we're conducting for Ventura County. I mean, personally, my hope is that individual groups with specific questions, from the sectors or from the ag community, from the water districts, could really think about how can we push this study to another level. I mean, kind of like Nina and Ben said over and over again, with climate modeling, the more money you have, the more better resolution you have, the more details you're able to be given. And so I think as we come up with, what is the validity of spending a chunk of money on a specific climate model so that we can save more money in the future by not having, dead crops or 0 acre feet of water, what does that cost to you, right? I mean, and so I think we're going to try as much as possible with the amount of funding that we have to answer as many questions, but at the same time, we can't answer them all. And I think the second question in terms of Henry with vulnerabilities is, I think Nina and us have had a number of conversations about that. In Ventura County, the vulnerabilities, you can rattle off a bunch and they're not really going to change, right? Fire risk, water supply, ecological, whatever. I think in terms of ranking vulnerabilities, is a social exercise, is what does it mean to you as a stakeholder, and every stakeholder is different. It's different for Arnie at WPD, it's different for you at Cayugas. And so I think what we plan to do is, with this background climate information, we give it to you, then we have that social discussion of how do we prioritize which are the most important in the watersheds, and how we tackle some of the issues, which issues to tackle, which ones do we have funding for. I think that becomes that vulnerability exercise that we have to do in order to satisfy the Irwin plan. And so that's kind of the next step, like Lynn said.
Yeah, and we do have the, once we understand more about what everyone's doing, what their particular interests and concerns are, when we go to look for research funding, we can work with you to develop research proposals that focus on your work, and that's becoming more and more common when you're applying for research funding, is do you have a stakeholder that you're working with, and are you supporting a specific stakeholder need?
Yeah, Steve Colomé. I'm an air quality advisor to the city of Ojai and to Citizens for Responsible Oil and Gas. First, I'd like to say it's a real pleasure hearing real science being presented. I have enjoyed this tremendously. My question relates to the coupling of the climate models, which are really becoming amazingly convergent. And that's reassuring in terms of the science. It's a little frightening in terms of the implications. But for temperature increases over time, we know, for instance, that electric demand is largely driven by air conditioning, particularly peak temperatures. To what extent can we now take these climate models and, for county planning purposes, look at a coupling of what this means for energy demand and grid and pattern and times of peak demand? Similarly, you can look at public health outcomes like deaths from extreme heat events. There's a lot of data on that could be coupled in. And in terms of air quality, we know that ozone concentrations are exacerbated by temperature increase. And again, that could be coupled in on the models.
Yeah, so for the ozone question is, I think, quite a bit easier in regards to, because we can just do the calculations, and you can sort of, have your model of how much ozone is being produced, or ozone precursors are being produced, and then as a function of temperature and solar radiation, start to figure out estimates of ozone production. Public health outcomes are a little bit trickier because getting that data sometimes is easy, and sometimes, as we have a project on heat extremes and health risks, and in, San Diego and I want to call it the Mexicali Baja National Mega Region. There's some crazy name. It's basically a Calexico, and we can't get the data yet because we don't have the HIPAA certification. So that can be a little bit of a limitation, but it's certainly possible if you can get it, to start looking at historical relationships and calculate heat index, which we didn't show any relative humidity, which is very important in heat index calculations, but there are models, downscaled models that do have relative humidity, so we could start to look at that. What I've found with energy demand, at least in Nevada, where I've done some work on urban heat island and energy demand, or tried to do energy demand, is that the energy purveyor did not want to share any of that data. And so that's a major limitation, is actually getting, I just want to make a scatter plot of maximum temperature and energy demand, and I can't do it because they won't provide the data, which I think this is a good venue for getting contact with people who say, oh, well, this would help us, we can help get you that data. So for basically all three components, we're more than happy to provide whichever kind of output would help you in the best way estimate future ozone production as a function of ozone precursors or population or what have you. Use historical relations of heat, health impacts, and energy demand as well. So I think it's all there. It's oftentimes the primary limitation is just getting access to the data of need.
Hi, I'm Brian Stark, Ohio Valley Land Conservancy. I'm wondering if your models calculate like temporal changes in when rainfall might happen, like are wet seasons getting shorter?
Yes, so and I do actually have, I can use my backup slides, bullpen slides. There we go. So dry season length we can calculate because the models are daily and they run essentially from 1950 to 2099. And so we can start looking at a calculation just like that where we can say, we could pick a dry season length of any threshold that you'd like, say 10 days or 20 days or 30 days, and we can go through each year and count up how many of those there are. What I did here, just as another kind of example, is look at the change from historical in the average maximum precipitation-free duration. So essentially, this is kind of that long duration period is going to be the date of last rainfall, because we know we don't get hardly any rainfall in the summertime, except in the rare tropical cyclone that makes it up here. Essentially, we're looking at the final winter season, cool season rainfall, and the first fall season event. And you can see a little bit more spread than some of the other characteristic of precipitation. Some models do not show much of a change, sort of the one at the bottom left-hand corner. The one on the bottom right-hand corner shows an increase on the order of maybe 10 to 20 days in certain regions. And then we know that one in the upper right-hand corner is the very wet model, and we can see that one's actually projecting a shortening of the dry season. So we'd expect a smaller amount of time between first and last precipitation event. And then the one in the upper left kind of mixed a little bit. I'm not sure why it thinks it's going to rain in Ventura and not in the mountains. This is why we look at more than one model. But so we can do that calculation, and if there's a number, or if you are really interested, say for planting of oaks, and you say, I really need to know what the dry season length or dry spell length between, say, March and June is going to be, we can subset that window and we can count up runs of dry days and precipitation, and we can set thresholds, and we can say maybe a quarter inch of rain won't make a difference. We need at least half an inch of rain, and so we can calculate the duration of time between half-inch increments of rain.
Also estimate or model somehow that time between this storm and that storm?
Yes, yes. So
like for seeds, if you put seeds out, they germinate and all that.
yes, so we can calculate dry season length, dry spell length. We can take when rain, the average, and I did do that calculation. I don't think I showed it. Nope, that's the minus. That's the near future and late century. I did look at the median change in dry day duration. So if you just take, for any given year, you count up how many runs of dry days there are, and you calculate the average and then the median lengths of those. We can look at those kinds of calculations as well. And if there's a set window of when planting could begin as early as this day, and we won't plant past this day, we can subset those windows and look at the average dry day, dry spells, the worst dry spells, and kind of hopefully help bracket some of the potential. Yes, yes.
Hello, I'm Kyle Maxwell. I'm the fish habitat assistant for the California Conservation Corps Camarillo Center. I have a question on some of the modeling. Have you ever used some of these climate models to like really predict in like in the really local areas, like in particular, if you're looking at more watersheds or even individual rivers and streams, like I'm trying to predict some of the temperature and or maybe even the stream flow, especially when you're trying to figure when you're trying to do mitigation efforts for endangered species. Like for me, it would be the Southern California steelhead trout. So have you guys done stuff like that before, or maybe plan to or something?
Yeah, so I have worked a little bit on some approaches to transforming global models to the regional scales where we can actually use them to drive either a hydrologic model or a streamflow temperature model. Haven't done it here, and I don't think, I mean, it depends on the scale of the watershed, but so this output I don't think is quite fine enough to really be where, like, what we would be really happy with driving a small watershed model with. A much larger, the scale at which this information exists, I'd feel a little bit better about it using it for something like the Sacramento River Basin, but the scale of the watersheds here is such that we may want to look into another subsequent downscaling type step, which may work better, may not, but at least it would better capture some of the terrain that we know is going to be very important for the scales of the watersheds here. So it's definitely something that we could do. And I have a little bit of experience in the past doing, but we aren't currently doing that. Hopefully that kind of gets.
Just a quick follow-up. Have you ever used just the data from the predicting future climate variabilities and stuff for just other endangered species? Have you actually used it before? Not just mine, but just with any of them before? Just out of more of a curiosity.
Yeah, I haven't. Although that's really a key goal with developing these kinds of downscaled projections, is so that you could conceivably say, I have an endangered species I'm concerned with, and I can't use, if all that whole box was one value of temperature and precipitation, that probably won't help you very much, but if we can get it to a scale that you can start addressing questions of interest, that's, I think, would be an excellent goal to do, but I haven't done it myself.
Okay, I think we have time for maybe two more questions, quick two questions here, and then I want to do just a very quick update on the IRWM plan amendment process before we adjourn. And then you guys are here for a while, so if you have questions after we formally adjourn, please feel free to stick around, and then see me or Poe if you're interested in going to one of the smaller meetings that are going to be held over the next couple of days with some particular focus group stakeholder areas. And you're here until, I mean, even as late as Thursday morning, perhaps. They're available to us to help kind of have these conversations so we can discuss that.
Thank you for these maps. In terms of your model, as a resident of East Ventura, the lower left one is interesting. So I wanted to ask you, in terms of the modeling, what land cover changes would make the most difference so that it would be more likely to get precipitation if we're close to the edge?
That's a good question, and
why is it showing this?
Or how would you deal with what it's showing?
Well, there's the basic question of how do we change land cover so that we have more rainfall. But specifically in terms of your model, what would have made that red either white or green?
That's where the downscaled model that we're looking at here, what you can do is you could actually go into that model itself and look at the model's representation of the precipitation processes and the conditions under which precipitation or the lack of precipitation is taking place, and you can start to see is the model realistically, should it look like that because of a realistic process? Maybe there's, maybe this is being driven by more, this model in particular maybe is producing more summertime thunderstorms for some reason or another. And maybe that's what, and those thunderstorms aren't able to shift as far inland, but they're able, for whatever reason, to impact the Santa Ynez and San Rafael Mountains, but they're not moving into kind of the, I guess that'd be the headwaters of several of the basins here. So that's one kind of hypothesis you could look at. So we can dig into potential drivers of it. My guess, looking at that, is it's probably not as much a land surface characteristic as it would be a terrain characteristic. That said, you could certainly, and I don't have the capability to do this because I don't run the model, but you can play games with the model and change land surface characteristics to see if we change the vegetation type or if we change the characteristics of the vegetation. Those kinds of things can feed back to increase or decrease precipitation. And then you could kind of take the flip side to that and say, if that's what the model is projecting, what could we do to change it to mitigate that? Maybe we plant something different or change the land surface characteristics in some way, rerun the model and see if that kind of makes the whole thing green or makes or smooths out that brown.
So more succinctly, if it's open sand now and it was gallery forest along floodplain, would that make a difference for your model?
It may make a difference. In the one big limitation with the climate models is the scale at which they're run. They often have to, we call it parameterize, which is really just kind of a way of saying we sort of smear out what's going on with different processes, and land surface models, which are part of the global climate model, is full of parameterized characteristics where we say, we just kind of bulk say there's this much leaf area index in the given grid cell, and we know that there's not that much leaf area index in that grid cell in reality because there's all kinds of things going on. So that's something you could do, but it's kind of a much larger, it's almost like a career's worth to just improve the representation of snow or forest types and forest heights and actually capturing the true mosaic of vegetation and how that impacts the atmospheric circulation and the precipitation.
One more follow-on. So if there was water in the river for longer periods of time, would you expect that there would be more trees in the floodplain of the river?
Probably, yeah. We had more riparian vegetation. And that's, yeah, and you can start also looking at things like if you have more vegetation, how does the water balance work? Are we losing more water because of evapotranspiration than we gain because of some other precipitation mechanism that could be started by having that vegetation? And you can kind of look at different outcomes with that. And there's a lot of work, I'm not super familiar with it, that focuses on those kinds of approaches for urban areas to really see about urban tree canopy and how that impacts evaporative demand or urban heat island or even air pollution in urban environments. So definitely is possible to do, although I personally don't have the expertise to do it.
Hi, Kit Stoltz. I write for various publications, report. Most of your presentation is about extremes of heat and precipitation and drought. This implies that annual averages are less useful. And if you talk to people like Lynn, they will say, with rainfall, there is no normal anymore. Is there a numerical measure of how much less useful the annual average is? Or
we're going to take a vote.
Or do we just have to wait 30 years for the climatology to roll over?
About that. So when I showed the example for Santa Barbara County, and our whole point of doing that study and breaking it up into what we called dry years and near normal years and wet years was not to use the 30-year average as our baseline because we see such high interannual variability. The 30-year average is actually pretty high and don't hit it that often. So we instead, going off some work that had been done previously used an approach. We tried several different approaches, and the one that we used that that captured what the impacts were the best, as we know, that water year 1969 was very wet, and water year 2005 was very wet in Santa Barbara County, and so the approach that captured that the best was to use the median as the baseline. So that's often a better approach, and then instead of calling above or below some threshold normal, having a range of what's normal, and then wet going outside of that range in the upper quartile and dry going beyond that. Unfortunately, that becomes much harder to communicate to a broad audience, and those 30-year averages are based off of work done out of the National Centers for Environmental Information, which are based in Asheville, North Carolina, whereas you saw in one of the plots, their interannual variability is quite low. So it's hard to be all on the same page as a nation of how we express departures from precipitation, but we're in a place where we have this much greater variability. So it's really tough. We want to speak a common language, especially when we go talk to decision makers who are East Coast based, but we need to represent our variability. So when we're working with the National Weather Service or us as the Climate Center, we're really pulled from, we don't want to talk about above or below a normal, but that's a very simple way to talk about it. So it's becomes a social and an actual physical manifestation of precipitation issue.
Yeah, and I guess, so especially the temperature, and where we looked at the greater than, or the top 2% of minimum temperature days, that's kind of biased high because my baseline period was picked to be the 1950 to 2005 historical period. And if we base those number of high percentile days based on that future period's climatology, we would see the percentile temperature value would be much higher, but compared to we'd see it just as frequently for that temperature value as we'd see in the historical period. And we know that as time goes by, if it continues to get hotter, there is going to be some natural adaptation of our, what we perceive as hot. And talk to someone from Phoenix, well, 107 is not that hot for them, whereas we're like, whoa, that's not so fun. And so it's hard to kind of capture that as well. But I think by showing what we today feel is extreme, how much more often that temperature value will take place kind of gives us at least a way to go, whoa, it's going to feel like that much more. I'll probably get used to it to some degree, but it'll still not be so much fun. But 30-year averages, there's definitely, as Nina was talking about, it's difficult because when we have huge variability, especially in precip, it's extra difficult. But then we know that temperature does vary on decadal scales and much longer time scales. And so I think the idea with the normals is really to give us a baseline of what's recent and what we've been kind of used to experiencing, which with precip and notably water allocations, which were all based on actually a very, very wet period, Colorado River as a prime time example, doesn't work so well when things change as time goes on, but it gives us at least a baseline to look at, and then we can shift forward like the new, what's it going to be, 2000 to 2019 or whatever the new 30-year normal? 1991 to 2021, there we go, 30 years. So we're going to stop seeing as many hot anomalies on the temperature anomaly charts because now the baseline period is warmer, whereas right now where we're using this old baseline, everything's red all the time, and it's more surprising to see a cold anomaly. But as we shift forward again, you're going to go, I actually see blue anomalies, cool anomalies, but the baseline is warmer. So it kind of blends into the social perception and reality challenge.
Well, this has been really incredible. I want to thank them again for coming.
And thank you guys.
And more importantly, for being our partner going forward in all the additional work that we want to do with you. And I can see possible other grant-funded efforts, and we'll all work together on that. And about a month ago, I sent out to the Watersheds Coalition list a link to the fourth assessment, which both of you have referenced and I think had a role in preparing parts of. That is actually really an incredible resource. It's 52 documents, I think. There's a summary, an executive summary, which is easy to wrap your mind around if this isn't your area of expertise. There's also a couple of those region reports throughout the state, and we have been linked in with the Los Angeles region. Very little mention of Ventura County in that section, but there's also the Central Coast section, which has, I think, a little bit more similarity to us in some ways, so I'm encouraging people to look at both of them. And there will be there's an LA-focused meeting coming up in Long Beach on November 2nd to sort of talk about that region report, which I think it behooves all of us to better understand what's in that as well, because there's a lot of additional data. Some of the questions came up today are also kind of addressed there, like Sacramento is expecting to have up to 40 by 2100, 40 days over 100. I already thought it was that bad up there, but guess not. So there's just some trends and some information presented in there that I want to encourage you to look at. There will be a Central Coast meeting as well, but that hasn't been scheduled yet. So I just wanted to make a plug for that document, and I guess they're already starting on the 5th assessment, which, you know, paint the Golden Gate Bridge, you start on one end and then go back and start again on the other end. We've already pretty much covered what we're trying to accomplish in the IRWM plan. We've had questions and discussions about that. The first step, and an important step, is of course the vulnerability assessment, and as Poe mentioned, some of that's sort of sociological. We're going to be doing discussions at the watershed committee level over the next number of months to drill down a little bit on that. But really the work that we're doing is regional in scale, and we're going to be working closely with Nina and Ben to kind of take the next steps. And so everything that happened in today's conversation, and we did record it partly because then we can go back and reference some of that, and I know I didn't take notes of everything that was being said, so I'll appreciate having that. We want you to continue to provide us with input, and so please, when I send out an email, if you have additional things you want to ask, and we'll also, I guess I'll talk to these guys if they want to be getting individual emails from folks, or if you want to funnel through us to you. And then we'll be writing up a lot of this and sort of building on it over the next number of months. So that's kind of the process that we see happening. Now, it's been brought up by a couple of people, how do we pick projects for adaptation? And that's a really important question right now because we are actually in a grant cycle. Proposition 1, IRWM implementation grant funding is coming. And we're also updating our plan to include new projects. So most of you know we've got a call for projects out right now for the plan, and then we'll be following up with which projects would you like included in Prop 1, which is going to be sometime in the middle of next year. So we have a little bit of time. But as we look at our projects, the state is requiring us to take a look at, well, which are the projects that are going to be most adaptive for us based on what we've identified as our vulnerability. So stormwater capture, treatment, and recharge. I mean, there's maybe an example of something that we want to look more at. Drought resilience and what kinds of projects help us with that. Agricultural, water use efficiency. There's a lot of different things that we're already doing, so it's not like we haven't already thought about this, but we need to maybe kind of up our game a little bit on those projects, and whatever gets put in for our application for the first round of Prop 1, we do need to address how those projects either help mitigate or adapt or both to climate change. So that's, you'll see that in the project input form, that you are supposed to be looking at those issues and checking some boxes to get us further along on that discussion. And if we come to points where we have questions about how certain kinds of projects or the design of that project helps us, and we need maybe some guidance from you guys, because I've already heard questions today about how do we drill down into the models and maybe help us answer some of that. We have their expertise to help us do that. So those are some critical things that we need to do. There's a lot of other climate change requirements in the guidelines for Prop 1. Some of them are fairly easy for us to just sort of pull things out of the fourth assessment or out of the presentations that these guys have made. But the hard work is in prioritizing our vulnerabilities, again, as they apply to different stakeholder groups. It's not going to be really possible for us probably to say the number one thing is temperature, because somebody else is going to say, well, no, the number one thing for me is precipitation. So we'll be looking at those issues. I think everything that you guys said today was, Ventura County, and the way I look at it, we're a laboratory of right now impacts. We just experienced the Thomas Fire. We have, potential for erosion-related events in big rain events, should they come. This is a great time for us to be doing what we're doing, because I think we have seen a lot of impacts across the county right now. And having your guidance in all of that is really helpful. So I think I'll end with that, and if you want to stick around and have a little conversation with these guys before they get too hungry and have to go get lunch, we have this room until 2 o'clock. And then there is the first focus meeting that we're having on what our stakeholder interest area on this is with the Watershed Protection District. That's going to be at 4 o'clock. Then we have a meeting at 9 o'clock with 10 o'clock with Casitas.
And then farm ag interest is at 11, and then at 1 o'clock is the groundwater folks focus meeting. 1 o'clock, right? And you know, I think the impetus for this is just to really get some sector-specific things that we're seeing in terms of urgency for discussion. You know, I anticipate that as we kind of go along, there will be future opportunities to have more special interest or sectoral focus groups. So stay tuned. We'll be reaching out.
So thank you all for coming, and we will be posting presentation and video at some point on the web. Room 346. Yeah. So any other last quick questions before we adjourn? Yeah.
It's more a question about, are you getting the feedback that you need from us, or do you need us to get a lot more specific about what sort of projects, like climate-related assessment and projects we've been struggling to fund that would help implement the work that we're doing on the watershed?
I think both. It's super helpful to just hear what is of interest and challenging and what your questions are. And we can certainly go as deep down the rabbit hole as need be to help you out. So super specific, I think probably the more specific the better, because the more specific, the more applicable to what you need is good. And you can send us homework assignments of read this 700-page document to know what I'm talking about, and that's fine too.
And we've had in this room today, I was looking around, we had representatives from most of our cities, from our Board of Supervisors elected offices, from the universities, from water districts, from groundwater sustainability agencies, from, you know, interest groups like the Santa Clara River Conservancy, the Naval Base. I mean, I think we've got pretty much the landscape covered in this discussion. So I'm really glad all of you came today, and we hope that you'll stay engaged in this. And we'll have another 1 or 2 opportunities when Nina and Ben will come back, and we'll have more sit-downs or presentations from them. And the ultimate outcome, at least in terms of incorporating this into the IRWM plan, will be a report that will plug into the plan, as well as using it to inform some of the other things we need to do. So again, we're really fortunate to have their involvement, and we really appreciate the Resources Legacy Fund and any other funds that come forward that want to help fund their efforts going into the future. And thank you, OVLC. Thank you all.
Thank you.
And keys, nobody ever came to claim these keys.